Nanomaterials introduction. So let's get us started. From the size of the airplanes to the height of the skyscrapers, engineering and trying to make our world bigger and bigger. But bigger is not always better. Sometimes we need to make things really, really small. That is why we need small materials, so-called nanomaterials. And we begin our journey to nanoworld, and we will talk about the reasons for the very special properties of nanostructured materials. So let's start with basic terminology. First things first. You heard about nanotechnology, nanomaterials very often, especially in some films, science fiction. So it's very popular term, actually. But what nanotechnology is? It's the science of manipulating atoms and molecules to make advanced nanomaterials. Humans started with the Iron Age or even earlier trying to make some tools to investigate, to manipulate the materials. And now we have the chance to discover the new worlds, nanoworlds, and manipulate on the very, very tiny level. So the basic building block of the material is atom. It's not chemically divided into some smaller parts, but atoms group together and they form molecules as a group of two or more atoms that form the smallest element. But these elements still retain the composition and chemical properties of the substance. Advanced nanomaterials are new materials with enhanced properties designed for superior performance. And we will learn a bit about the applications of nanomaterials. And we cannot say that nanotechnology is the part of some specific science like physics or chemistry or engineering. It's everywhere. And usually it's some combination of the knowledge in different areas. So it's still emerging, but it's absolutely interdisciplinary field. And we use this word nano. What is actually nano? What does prefix mean? Nano is the millionth of a millimeter or a billionth of a meter. So it's pretty tiny. For example, one period or a dot is about 1 million times bigger than 1 nanometer. Human hair thickness is more than 50,000 times higher than 1 nanometer. But to make nanometer from atoms, we need at least 10 atoms side by side to make up. You can see it's in nanoscale. So we consider something which is even smaller than virus, bacteria, or some antibodies. Nanomaterials are classified in some groups. Actually, when we're talking about nanomaterials, it's materials in size range from 1 nanometer to 100 nanometer. The classification is based on the number of three dimensions. Sometimes it is misunderstood that 0D, 1D, it means the number of nanodimensions, but it's not true. 0D nanomaterial, it's material where all three dimensions are in nanoscale. So there is no kind of free dimension. So there is no dimension which is out of nanoscale. So 0D materials in all three dimensions are nanoscale. The examples are nanoparticles, colloids, quantum dots. 1D, one-dimensional nanomaterial, has one dimension outside the nanoscale and two dimensions in the nanoscale range, like nanowires, nanorods, nanotubes, and biopolymers. 2D nanomaterials is when any two dimensions can be outside of nanoscale and one dimension in nanoscale range. They exhibit like plate-like shapes, like thin films, nanolayers, you may see here in the pictures, the bottom. And 3D nanomaterials, they are not kind of bulk counterparts, but they are still nanomaterials, but they composed of nanomaterials. They have all three dimensions outside the nanoscale. But again, it's not bulk. It's made up of nanomaterials. It could be the bundles of nanowires, nanotubes, or simply, as you can see here, it's a multiple multiple nanolayer. We should understand that there is a wide spectrum of different morphologies of nanomaterials. We still divide them based on the number of three dimensions, but the morphology can be explained as a combinations of geometric characteristics. For example, we can divide 0D nanomaterials into core shell, encapsulated, or nanocomposites. Likewise, to design and develop heterogeneous nanostructures, it is important to choose a perfect source material for getting appropriate nanostructure of particular importance. A comparative statement based on the structural complexity of various heterogeneous nanomaterial is classified into four major categories. That's what we can see here. The combinations of multi-nanocomponents are available in the heterogeneous nanostructures, each of them tailored to address different needs. It could be high conductivity, excellent mechanical stability, high energy density. So the choice of this modification is based on our need. In consequence, the composite materials will exhibit synergetic properties. They provide lots of benefits and act as a promising material. In contrast to previous model of nanomaterials, now we have a possibility to see the image of real nanoparticle, single composite coat, but there is the problem. What is the condition for obtaining such images? We cannot just take a look at these through the optical microscope or whatever, because the average wavelength of visual spectrum of light is about 500 nanometers. These are green lights. So the optical devices that operate in visual range of spectrum cannot be used. Again, we're talking about nano materials. So it's like from 1 to 100 nanometers, and the wavelength is 500 nanometers. We have a possibility to see the image with the use of transmission electronic microscopy. So if optical cannot be applied, so we discovered a new method to see really tiny materials. The electron beam propagates through the material, and the difference in the number of electrons after absorption by this material is recorded as a contrast between different points in the image. Like you can see here. So we actually can not just imagine, we can see the nanoparticles. Single nanoparticle, nanocomposite. So it's like the contrast image gives us these pictures. Similar images for one-dimensional nanomaterials as nanowires, nanorods, or nanotubes. Again, we got this using TEM, transition electron microscopy. You will have the possibility to get detailed information about different types of carbon nanomaterial. They can set aside because of their very unique properties and the wide range of allotropic modifications, as you can see here in this picture. But now you can only compare structural variability caused by the special electronic properties of carbon. The more about carbon nanomaterials, you will hear the following lecture, which is dedicated to the graphene and other carbon allotropes. You may think that nanomaterials is something new, something like 21st century, brand new branch of science, but actually it's not quite correct. The first application of nanomaterial dates back to ancient time, like 1,000 years before electron was actually discovered. For example, you can see here, it's the Lycurgus cup. It shows the mythical king Lycurgus who tried to kill the follower of Dionysus. It's like mythological king. It depends on different version and other stuff. But what is interesting about this cup? Roman glass workers produced glass with different colors in transmitted and reflected light due to the presence of some a small amount, actually from some nanoparticles, gold and silver. actual nanoparticles. These particles precipitate as colloids and form an alloy of silver and gold. When viewed in reflected light, the smallest metallic particles are large enough to reflect enough light without obstructing its transmission. In transmitted light, on the other hand, small particles scatter the blue end of the spectrum more efficiently than the red end, resulting in the rendering of the red color, which is what is observed. So you can see it as green or red, all depends if it's reflected or transmitted light. It is impossible that Roman craftsmen managed to add such an incredible small amount of silver and gold to volume of glass. So we actually scientists think that it was done by mistake, accidentally. Nevertheless, it's a colloid of nanoparticles and it has pretty interesting properties. The same approach was used by the medieval masters for fabrication of beautiful colored window glass, as you can see here. So just imagine the glass and gold have pretty similar melting temperatures, and the masters only mix these materials with different intensity, manufactured glass of different colors due to the particle fragmentation. Different size of nanogolds produce different colors of glass. Particles around 20 nanometers produce red glass. Particles around 30 nanometers make this like paint glass. And the particles of 80 nanometers produce orange glass, and so on. So the size of this gold nanoparticle really influence on the color, and we will talk more about gold nanoparticles because it's pretty interesting. Another known example of the late nanotechnology is Damascus steel, with fiber-like nanoparticles of iron carbides, which made the material flexible and exceptionally strong. Michael Faraday tried to explain, actually he has explained the color of stained glass window from the presence of metal nanoparticles. He prepared the red-colored gold that you may see here, red-colored gold nanoparticles, which still stable after more than 160 years. It's preserved in London in the Royal Institution. Only in 20th century, the special optical properties of gold and other nanoparticles were explained. The color of gold nanoparticles changed based on their size and shape, as I already told you. As the size of gold nanoparticles decreases, their color changes from yellow to red, then to blue, and finally to violet. You may see here also. The different colors of nanogold come from a phenomenon called surface plasmon resonance. So nanoparticles of gold resonate at frequencies within the visible spectrum of light. Smaller nanogold particles absorb and resonate with purple, blue, green, and yellow wavelengths of light, so they look red. Larger nanogold particles absorb and resonate with green, yellow, and red wavelengths, so they look blue. And it was like explained by Gustav Mie in the beginning of the 20th century. Richard Adolf Zsigmondy in the first decade of the 20th century studied the optical properties of gold either, and not only gold, but other nanoparticles. And he received the Nobel Prize in Chemistry in 1926 for that studies. So we know that it's not new, the use of nanotechnology, nanomaterials, but as in other fields of human knowledge, the nanotechnology has its own founders. One of them is famous American physicist Richard Feynman, the genius theoretical physicist who was a member of the Manhattan Project and nuclear bomb fabrication, and also the author of famous speech, "There is plenty of room at the bottom, an invitation to enter a new field of physics." It was a lecture given by Richard Feynman, an annual American Physical Society in 1959. Feynman considered some ramification of a general ability to manipulate matter on an atomic scale. It was 1959. He was particularly interested in the possibilities of denser computer circuitry and microscopes that could see things much smaller than is possible with scanning electron microscopes. These ideas were later realized by the use of scanning tunneling microscope, the atomic force microscope, and other examples of scanning probe microscopy, and storage systems such as Millipede, created by researchers at IBM. He also presented, which is pretty interesting now, the possibility of swallowing the doctor. It looks like some science fiction, but this idea, um, which was created in some essay to his friend, was firstly used in that around this time, 1959. This concept involved building a tiny, swallowable surgical robot. Another ideologist of nanotechnology is Gordon Moore, who made a forecast, you may see here in this graph. What forecast? It's for nanoelectronics development. According to Moore's law, the number of transistors on a chip of given area would double in every 1.5 years, which means that the dimension of a transistor size must be decreased by factor 2 in every 1.5 years. This relationship was formulated in 1965. And according to this prediction, the average size of transistors of the modern chipsets should be about several nanometers. This is true. But you probably know that we already achieved the threshold of the next shrinking of electronics components, and the further shrinking is now considered pretty impossible. We should change the concept for the next development. The main idea of these changes is the transformation of quantum mechanics from theoretical physics to applied physics. One of the last remarkable discoveries in nanotechnology is obtaining graphene by the scientists Game and Novosolo, and they were awarded with the Nobel Prize in Physics for this discovery. You will learn more about graphene materials and graphene-like materials in the following lecture. As we understand, properties of material describe how materials work under certain conditions. For example, large or bulk zinc oxide particles block UV light, but scatter visible light. As you can see in this picture, we can see this cream on the face. As like we can see Snow White, because it effectively scatters all wavelengths. When we use zinc oxide nanoparticle, the ultraviolet absorption properties remain, but the oxide particles become invisible in visual range of light. So we have novel sunscreen, which we cannot see at all. Another example is carbon nanotubes, which electrical properties change with the diameter, twist, and number of walls. They can be either conducting or semi-conducting in their electrical behavior. So both size and morphology matter. It's pretty important that for nanomaterials, size matters. What are the reasons for the special properties? Before we consider the applications, their use in different fields of knowledge, we have to understand what nanomaterials is and why it's so unique compared to bulk counterparts. To understand this, we have to consider some classical and quantum properties. So, first of all, it is the increase of the surface to volume ratio. As you can see here, the cube can be cut in some number of pieces. For example, here, 27 pieces. And it leads to triple increase in the specific surface area. So 6 becomes 18, so it's tripled. In transition electron microscopy images, you can see examples of porous carbon and lamellar particles of graphene with the extremely high specific surface area, up to 3,500 square meters per gram for activated carbon. So making it smaller divided the bulk material into smaller parts, we rapidly increase the surface area. And it's pretty important in the explanation for the reasons of the special properties of nanoscale materials. The second is the surface tension effect. As a sample is made larger, a smaller fraction of the atoms are on the surface. Atoms in the surface have fewer neighbors than those in bulk. We can compare it to the students at the edge of the classroom. They have fewer neighbors than those in the middle of the classroom. Only atoms on the surface can interact with another material and take part in chemical reaction. So reactivity increases with increasing the surface tension, the surface area. Superficial layer has an excess energy, and this energy called surface free energy, in comparison to bulk. Decreasing of the particle causes the fast growth of its surface energy that leads to change of the properties due to appearance of special tension that is inversely proportional to the particle size, as you can see here. The next component, or the next side of the problem, the reason for the change in properties, is the size effect, which can be observed when particle size becomes close to some characteristic length of this material. One of the examples, because there are lots of different properties that change, but one is pretty interesting, is the melting point. So melting point is the temperature at which the atoms in a substance have enough energy to overcome the interatomic forces that hold them in a fixed position in a solid. At macroscopic length scale, the melting temperature of materials is size independent. So when we consider a small ice cube and you consider the glacier, both of them will melt in the same temperature, because still there's a macro objects. Surface atoms require less energy to move because they are in contact with fewer atoms, as we already mentioned. So the decrease in the size to nanoscale causes the increase in the surface energy and decrease in melting temperature. So the higher surface area means the lots of atoms they need fewer energy, so can easily overcome this threshold. So heat is transported in materials by two different mechanisms. It could be lattice vibration waves called phonons and free electrons. Size effects will be observed when particle size becomes close to the length of run of photons or electrons. So when they are close in size, we consider the size effects. So this approach can be applied for different property changes, from chemical to magnetic. We already mentioned how the change in the size of gold nanoparticle influence on their appearance. So to understand deeper the problem, we should consider the basics, the very, very basics of quantum physics. It's nothing too complicated, just to make an overview, even though the quantum mechanics, quantum physics appears something pretty complicated. But they date back to the age between 19th and 20th century. At the end of 19th century, scientists thought that they discovered everything possible, and they explained every properties of the material using physical phenomena and so on and so forth. But then they faced the problem of description, for example, the atom, how atom looks like, what atom is. There were lots of models, and all of them were incorrect or partially incorrect. So there were many problems when we proceed to the quantum level, when classical physics simply doesn't work. So quantum physics is needed to understand what the atom is, and especially to consider some absolutely crazy idea that atom is an electromagnetic wave. So first, according to the Rutherford model that you can see here in the slide, according to the Rutherford model of atom, the electrons are like planets in solar system. where the sun is a nucleus, but classical model has a large problem. The electron has a negative charge, we already know it, and it orbits around the central positive nucleus. Positive, so it has charge either, and therefore has magnetic field. Charged particles lose energy as they pass through the magnetic field. It's a fact. But according to classical electromagnetic theory, the electron should lose the energy in its orbit and eventually drop to nucleus. But we cannot observe this. It's not true. At the same time, the atom is stable, consists in some subatomic particles that not normally decay our lifetime. So there are two options. Either classical physics is wrong, or the Rutherford model is wrong, or incomplete at least. So we have this problem, and this problem was pretty sharp in that time when scientists began to believe that classical physics doesn't work. But it's not true. It works, but on macro scale. As quantum physics can be applied in the macro scale either, but there is no reason for it. It would make our life pretty complicated. So both classical physics and the quantum level and the Rutherford model have some problems, some minor problems, but is in our picture of atom is mostly incorrect. The answer, the solution to the problem was found at the beginning of 20th century by Max Planck. You can see in this picture with the highest IQ ever. This was called like ad hoc. Ad hoc means he solved the problem, found the solution particularly for this problem. So it was not understood theoretically. It was not. It was something absolutely new, and it was even hard to believe that it works. But it worked ad hoc. So energy is not a continuous stream, but consists of chunk of discrete packets. Energy is quantized, so it means that it flows as quanta. Each quantum of energy can be determined using this very simple formula, where E is the energy of the quantum in joules or electron volts, F is the frequency of the vibration, and H is the Planck's constant. Planck constant is very, very, very small. So when we have these energy levels, but as these Planck's constant is so small, it means that the current distance between energy levels is so small, we cannot observe it on the macro world, but only in the quantum level. But what is vibration? So according to Bohr model of atom, the electron in an atom moves in a circular orbit around the nucleus. And here we have, it has mass, speed, and in this orbit, it has radius, and as a result, the electron experiences a centripetal acceleration toward the nucleus. And we know the magnitude of this acceleration. From Newton's second law of motion, we know that force can be defined right here, is required to produce acceleration. In this case, the force is the electrostatic force, where K is the constant. Combining these results here, and the second, so using this simply the second Newton's law, combining these results, we have this relationship. And then Bohr assumed that the angular momentum in an allowed orbit must be an integer n times Planck constant over 2 pi. So Planck constant over 2 pi, and this is the angular momentum. So there's a condition will look like here. So the angular momentum equals n, which is some integer number, times h over 2 pi. Sometimes this h over 2 pi is denoted as h bar. Using all these, combining this, the force angular momentum equations, we can solve this equation and find the radius here. And what do we see here? The radius, we have this constant mass, k, e, and so on. And this, we have this n integer number. Whereas what is integer? 1, 2, 3, and so on. What the conclusion? So the only Saturn orbits are allowed. It's not continuously changed. It has some certain set of these numbers. And this only the beginning. The total energy of hydrogen atom is also quantized. In fact, a straightforward calculation combining both the kinetic energy here, mv squared over 2, and potential energy here, they show that the total energy of the nth Bohr orbit looks like this one. So as all of this is constant, so it's like negative some constant, our n squared. So again, n is integer number, so we have some set of energy values. But the question is, what does negative energy mean? Why it's negative? We can imagine the electron in atom as a ball in a well. The potential energy of the ball is measured with respect to the ground. So like the ground energy is kind of 0. Then when it moves into the well, it becomes negative. So the maximum energy will correspond to the bottom of the well. So this we can imagine the electron in atom. So this quantization of energy levels, the orbits, and the energy is quantized, the radius is quantized, and so on. The next step is oscillation. So what is oscillation or vibration? Is a periodic motion when the state of the system repeats itself after regular time interval. So we can compare the oscillation of mass on the spring or pendulum to electron oscillation in atom. So we can use this classical concept to try to understand it on the quantum level. Parameters of periodic motion are period, frequency, and amplitude. Sometimes we use angular frequency as the frequency times 2 pi. Don't be scared. It looks pretty complicated, but it's really pretty simple. So if you perturb the spring from equilibrium and let it go, it will execute some harmonic motion. Pull the spring to the right and it tries to restore its length. So in equilibrium, we consider that there is no force, x is 0. So we push the spring to the left and it tries to restore its length. All of this can be summarized by Hooke's law. That's like school law for the spring, where k is the spring constant. So accelerated motion of mass on the spring happens because of restoring force. By comparing these equations, here, the Hooke's law, the second, Newton's law, we can compare, and then we will have the equation which is called differential, second order differential equation. So where the acceleration is the second order derivative of this position. And when we solve it, there is the pretty simple method to solve. We will have the solution of this differential equation, which is simply the combinations of sines and cosines. So sine, cosine function. So we see that it's harmonic. And as you can see here in this graph. So solution is the dependence between coordinates and time, as this you see here. In any moment of time, the full energy of the mass on the spring is a combination of its potential and kinetic energy. So for the mass on the spring, we have this simple equation, whereas this x dot is the first order derivative. Important notes: the dependence of energy on position is parabolic. This dependence preserves as transmission to quantum mechanics, so from classical to quantum level. But it will be not continuous as for the classical case, because it consists of some individual values. Each of them is described by this equation. You can see here. Whereas again, this h bar is Planck's constant divided by 2 pi. Let's image the quantum pendulum. Its trajectory isn't continuous, but it is like a series of leaps, as you may see in this animation. So the energy of an oscillator, like electrons in atom, can have only certain discrete values. So the energy is quantized. So each discrete energy value corresponds to a different orbitals and different quantum states. So we have some important, really important conclusion. First of all, electron on an orbital is equivalent to a standing wave distributed along this orbital, like here. It's like standing wave in the orbital. When electrons behave as the standing waves, they no longer emit energy. Since this applies to particles, this is the Broglie idea we will consider later. The change of electrons' energy is equivalent to change of the quantum state. Like here, it absorbs energy, like you see in this animation. Then it emits energy and come back to the previous state, to some non-excited state. The change of electrons' energy is possible due to irradiation or absorption. You may see here. So we see this very important conclusion. So we understand that our like description of atom, the Rutherford description was pretty incorrect. What about this de Broglie's idea? De Broglie made the idea that any piece of matter traveling at any speed can exhibit wave properties. So not only we consider the light as a particle or a wave, not only electron, we can consider any material that travels, that have material that has speed as a wave. The de Broglie wavelength of a particle is here. Sorry, this. So this formula allows us to find the wavelength of a particle, but they are too small to observe. You can make this calculation and find the de Broglie wavelength of a person with a mass of 70 kilograms traveling at about 1 meter per second. So when this age, we already mentioned that it's pretty tiny, it's 10 to the negative 23. So these wavelengths will be so small, even smaller than the size of an atom. That's why we usually do not consider the marker objects as the wave. But theoretically, we can. So the quantum particles, like an electron, is not only a particle, but also it has some wave nature. According to a number of experiments, the electrons can diffract. That is a proof of the de Broglie's idea, because diffraction, interference are the wave properties of the material. So this is the double slit experiment, and the following lecture you will discover more about it. So I just mention it. So this experiment showed that electron beams can undergo diffraction when passes through the atomic crystal. This showed that the wave nature of electrons as waves can exhibit interference and diffraction. So we have some typical question. What about a single electron? Will it be divided in diffraction? No, but we can try to answer these questions later. Then another principle is uncertainty principle. Uncertainty principle is pretty interesting in quantum physics. In classical mechanics, it is possible to make measurements with arbitrarily small uncertainty. So we can measure the speed or momentum and position of an object at the same time. It's not a problem. Quantum theory predicts that it is fundamentally impossible to make simultaneous measurements of a particle's position and momentum with infinite accuracy. So this principle was firstly formulated by Werner Heisenberg. You may see in the picture. The Heisenberg uncertainty principle states that if a measurement of the position of a particle is made with some uncertainty delta x, and a simultaneous measurement of its the component of the momentum is made with uncertainty delta P. The product of the two uncertainties can never be smaller than h bar over 2 or Planck constant over 4 pi. So it should be more than this value. Actually, but why? Why we cannot observe? This is the fundamental problem in quantum mechanics, is the problem of observation. So when you see, for example, this slide, how you see it. So the photon bounce from like strike this screen and bounce back into your eyes, and then you may see it. So nothing changed. You see it. But what if we consider this quantum level, this nano level, for example, when photon strikes an electron, it changes the state of the electron. So we can find its position, but we cannot measure the momentum. We cannot, in this case, observation can even destroy the particle. It changes. So when you see the screen, you cannot influence on this because this macro object, you just see it. It does not have any effect on it. But when you want to see, to observe, to measure the particle, you destroy it, you change its state. So quantum system, these are trajectories of electrons after diffraction are statistically uncertain. In classical system, the trajectories of electrons after slit are definite. So after diffraction, the single electron will choose one of the several variants, several options of the possible trajectories, and its choice is statistically uncertain. So this is this uncertainty. It's a probabilistic problem. So the next step is to consider the electrons in atom. There is pretty complicated problem to imagine how the electrons are rearranged in atoms, but each electron shell comprises the subshells, which in turn consist of orbitals. The electron system of an atom could be compared to a multi-story hotel. So we consider this atom as the hotel building. On each floor of the hotel, we have rooms of different type. All rooms within each class are identical, while they at the same time they're different from the rooms of another class. So our hotel building is an atom. Each floor is the atom electron shell. Each set of identical rooms, electron subshell. Each room, regardless of its type, is an orbital, and each guest in this hotel is an electron. So on the first floor is the first electron shell. So when n equals 1, which is the lowest in the energy, and it has only one room, which is spherical in shape. So only one room here. It's called S orbital. While there is only one room, and consequently only one type of room on the first floor, the second floor features a total of 1, 2, 3, 4 rooms. It's not the same. And the one room is the S orbital and 3p orbitals. So one of these is spherical and other 3 is the shape of the dumbbell. Orbitals of this shape are referred as p orbitals, but they look like identical, but they have different orientation. They're kind of perpendicular to each other. So electrons orbital, the part of the space where the probability of finding the electron is non-zero. So this is a space where we have chance to find the electron. So we still prepare for quantum size effect explanation. So now we can imagine the electrons in atom, and we understand that this animation is completely incorrect. The next step is the electrons in crystals. So we move from that quantum problem to the electrons in matter and eventually to the nanomaterials. There is the first idea. The ideal particle has zero size, therefore is localized in space. An ideal wave has a single frequency and it's infinitely long. So it's all about idealization. A localized entity can be built from infinitely long waves. Multiple waves are superimposed so that one of its crests is at zero, and the result is that all the waves add constructively at x equals zero. So there is destructive interference at every point except x equals zero. So the small region of constructive interference is called a wave packet. So you may see here, so we have the several plane wavelengths, infinite wavelengths, combined together, and we have some wave packets. So this wave packet can be identified as a particle. So the small in delta p, this momentum, we have only one wavelength. The medium, we have some packets. In the large, this looks like a particle. These wave packets. And when we proceed further to the condensed matter, so condensed matter physics deals with the systems of a large number of interacting particles and explores macroscopic behavior of matter based on its microscopic properties. So we need this bridge between microscopic and macroscopic properties. You already know these. The particles can gain their energy, either increase their kinetic energy and vibrate more. So it can go from the solid to liquid to the gas. And the interaction is different. So strong interaction in solids and like not so strong interaction between particles in a gas state. So it's all about the behavior of the macroscopic based on the properties and microscopic properties. Crystalline materials are characterized by the long-range ordered periodic arrangement of atoms. We know. For example, silicium oxides, sands for simple, this crystal consists of periodically ordered silicon and oxygen atoms with Saturn symmetry of special distribution. So this, the long range ordered. And then we order this microscopic object to get this some macro object, like this crystal you may see in the picture. So what is this all about? It's about the band structure formation. So each atom has these levels. But when we combine them, these levels combined, and we will get some band structure. So the magnitude of the neighboring atom's influence depends on the type of atoms. Each atom's surrounding, as well as the electron's location within the group of atoms. According to Pauli's exclusion principle, when the system consists of many identical atoms, the single atom's discrete electron energy levels change into energy band. They kind of combine together and form bands. So we cannot distinguish each atom, one atom from another, but we have some bands in the lattice structure. An energy band is an energy range with many allowed adjacent energy levels, very, very close spaced. An electron in a crystal is a periodic electric field, which is created by the nuclei of atoms, and electrons either in the shells of atoms. The electrons in a crystal experience a potential with a periodicity. The scale of this periodicity is of the order of the de Broglie wavelength of an electron, about 0.1 nanometer. So the periodicity is an idealization because we have some impurities, thermal vibrations, defects, but the Schrodinger's equation defines the position of the electron is both energy and time dependent. But we cannot find actual position. Schrodinger's equation looks pretty complicated, but it describes the electron using the wave function. It gives the probability of finding the electron in a given location. Already mentioned that it's all the probabilistic. We cannot find the certain position, but we using this wave function, which can be found using the Schrodinger's equation, which is simply the combination of kinetic and potential energy. When we solve this equation, we can find this function which describes the probability. So we can use it to find the probability of the location of electron in that in space. So it can be simply considered as the law of conservation of energy, even though it's pretty complicated to analyze. But our task is not to solve Schrodinger's equation or to deep into quantum mechanics. The next step is to understand that the wave function doesn't tell us where the electron is. So in classical physics it does, but not in quantum physics. It tells us the probability that the electron is here or there or somewhere else. To visualize, for visualization of a wave function, we can use this probability cloud. Max Born was awarded the Nobel Prize in 1954 in physics for his fundamental research in quantum mechanics, especially in statistical interpretation of the wave function. So, interpretation of the probability cloud is pretty simple. The electron is most likely to be found where the cloud is most dense. For the cloud in the above figure, the highest probability is the dark band, which is actually a spherical shell. The probability of finding the electron near the nucleus is smaller, it's pretty small. Probability clouds for excited states of hydrogen have the same interpretation as that for the ground state, but their shapes are more interesting. So we are talking about some superposition of these different wave functions. So we're talking that electron can be at the same, the few points or the different points of the space at the same time. It's a probabilistic. Everybody knows about Schrodinger's cat, at least some memes on the internet. But actually, Schrodinger didn't like this idea of superposition. He wanted to criticize this, and he tried to explain it using some theoretical thought experiment. But it was done actually just a fun of this superposition theory. So he considered a cat which is locked in some steel chamber, along with some device, which must be secured against some interference by the cat. So there is the Geiger counter. There is a tiny bit of radioactive substance, so small that perhaps in an hour only one of the atoms decay, but also with equal probability that perhaps no atom decay at all. So what we have some radioactive substance, which has probability to decay. We have Geiger counter, which start the mechanism that smash the ball with some poison. And then in this situation, cat dies. So there is you can see in the picture, when it detects this radioactive atom, it starts this hammer smash this flask of some acid or some poison, and cat dies. But before you open the box, you do not know if it's cat dead or alive. So in that time, it's kind of the superposition. So the cat is in the mixed state, in the dead alive state. So at the same time, it is dead and alive. Even if might like fun of this superposition idea, it's now very popular thought experiment which allows us to explain and understand this superposition. So the cat has some, the system has some this psi function, this described the previous slide of the system, which is express that The system is in living and dead state at the same time. The electrons in the same orbit exhibit different energy levels. We already know this. And we know that in atoms, in condensed matter, they all form some bands. So grouping of these different energy levels are called energy bands. So there are three types of bands, and based on this, we have three main types of the materials. So we have valence band, the energy band that consists of valence electrons. So the top of the valence band is gonna the maximum energy level where we have electrons, valence electrons. Conduction band is the energy band that consists of free electrons energy level. So it's like this, the empty. And forbidden energy gap is the gap between the valence band and the conduction band. So it's called the forbidden band or forbidden gap, or just simply band gap. The energy difference gives us this band gap, this energy difference gives us the information about the type of material. For example, in conductors or metals, the valence band and conduction band, they overlap. There is no band gap. There's a zero energy difference. For the semiconductor, we have the small band gap. And for the insulator, it's pretty big. So semiconductor is kind of in between conductors and insulator. That's why it's called semiconductor. And based on this band structure, we can see the difference between materials. So when, for example, semiconductor has some energy absorbed, the electrons can move from valence band to conduction band, and it gives its pretty interesting properties. There is some unexpected conclusion. So the space in which an electron exists is quantized, and it consists of individual cells, each of which can contain a maximum of 2 electrons with opposite spins at the same time. So we know it's the basic quantum physics. There is a finite number of such cells, and the crystal can contain a finite number of electrons. The jumping of electrons between the cells is equivalent to a change in their energies. So the energy of electrons is proportional to the square of some momentum, and it's increased in this momentum implies as the electron in some cells can be placed in these cells. So we can describe all of this using the density of states. You can see here in the picture. So the density of state is the number of different states, the cells, at a particular energy level that electrons are allowed to occupy. In other words, the number of electron states per unit volume, per unit energy. So we can use this function, this density of state, to describe the states of the electrons in the matter. When the length of a particle is reduced to same order of magnitude as the length of the wave packet, for example, to a few nanometers, the effect of quantum confinement occurs and the properties of materials are modified. So depending on the confinement dimensions, 3 types of confined structures are distinguished: the quantum well, quantum wire, and quantum dots. So the reduction of the dimensionality caused by the confinement of electrons from a volume 3D to a thin crystal layer 2D leads to radical change in their behavior and density of states. So this function changes when we move from 3D to at least to 2-dimensional material. Further reduction of the dimensionality of the electron's environment to 1-dimensional material, and finally to 0-dimensional quantum dots, leads to the formation of an atomic-like system. So this system is similar to atomic system. The energy of distribution of electrons in quantum dot is similar to the energy level of an atom. So all was above about the energy level of atom. Then we proceed to the condensed matter, to some materials. but decreasing the size of the bulk material to the quantum level, to nano level, we will get the quantum dot, which is the material which has some atomic, that looks like atomic-like system. So it looks like an atom. So there is no band structure, but the density of single levels is higher. Semiconductor nanoparticles are called sometimes artificial atoms because of their atom-like discrete electronic structure resulting from quantum confinement. So when we see that the atom, then we proceed to some levels, to the bands, valence, conduction bands as a semiconductor. Then we decrease the 3-dimensional to 2-dimensional, then 1-dimensional, and at least 0-dimensional. And we like move in this circle and goes to atom-like structure, 0-dimensional particles. Artificial atoms can also be assembled into artificial molecules or solids, and then it opens the new possibilities of manufacturing new materials. The nanoparticle size decreases from left to right, and the corresponding increase in the band gap occurs. So it's another characteristic is like photoluminescence. It's the color you can see from red to violet. The smaller particle has the higher band gap. And these changes not only band gap, but also the confinement width. And we decrease the nanocrystal, we see the change in the color. It's the system change. This is some semiconductor changes. And one of these is the photoluminescence. So we have lots of particles and they absorb and emit the light in different colors. The quantum dots, the fragments of semiconductor with the bulk bonding geometry and with surface states eliminated by enclosure in a material that has a larger band gap. So quantum dots usually contain from 100 to 1,000 electrons and range from 2 to 10 nanometers, sometimes from 10 to 50 atoms in diameter. The modification in the energy in this band gap energy of semiconductors is the most attractive one because of the fundamental as well as technological importance. So we can modify the band gap, and then rapidly change the properties of these quantum dots. So semiconductors with widely tunable energy band and this energy band gap are considered to be the materials for next generation. They used in photovoltaic, optoelectronic devices, the displays, lasers, photonic sensors, and so on and so forth. They have very interesting properties: the high extinction coefficient, high electron mobility, band gap and position tunability, solution process capability. So this changing that characteristic of the semiconductor can change their application, and we can modify them, these materials for our needs. Optical properties are the most important for application of quantum dots. Unlike bulk counterparts, bulk semiconductors, which have continuous energy levels within bands, the quantum confinement effects create a large band gap with observable discrete energy levels. So not continuous, as we can see here to the bulk counterparts, but with discrete energy levels. And due to this quantized band gap, a quantum dot can emit a very consistent wavelength of light that can be fine-tuned by changing the size of the quantum dot, or in other words, changing the energy levels. These images here allow us to visualize, to see the different geometry. It's a visualization of geometry of quantum dots as nanoparticles. So dots, rods, tetrapods, or other different shapes and different modifications, different structures from molecules to devices. There is the wide range of application of quantum dots. So we will talk more about application generally of nanomaterials. But what about quantum dots? As already said, it's like light emitters, photovoltaics, photoconductors. Also, it's biomonitoring, drug delivery, gene delivery, optical sensors. So this is the very wide, very large scale of the application of material. The one example I want to show you is about the screen's display. So quantum dots enhance the quality of images on the screen. So as you know, the RGB is used as a combination of three components, red, green, and blue. That's RGB stands for. Each component is emitted by individual source, and quantum dot-based emitters allows us to narrow the spectra, like you can see here, narrow the spectra to avoid this overlapping that we can see in some conventional displays, LCD, for example. So we do not have this overlap. We minimize this overlap, and it leads to clear and more contrast images. This is one of the applications. Another important phenomenon is quantum tunneling. It can be described as the quantum mechanical or nanoscopic phenomenon when a particle tunnels through a barrier that it cannot overcome, as classical explained. So classical physics says that it cannot happen at all. Its principle of operation is used in modern devices, such as the tunneling diodes, scanning tunneling microscopy, quantum computing. It is predicted that quantum tunneling will create physical limits on how small transistor can be, because the electrons will be able to tunnel past them if they are too small. This is seen as one of the new consequences of quantum mechanics and is basic and fundamental to nanotechnology. A few words about manufacturing of nanomaterials. So we understand the properties. We know these properties, we know these characteristics, how it's important to describe it properly, but how to manufacture nanomaterials. Numerous synthetic approaches are available for the synthesis of advanced nanostructure materials. A few of them will be described in the following lecture, actually. A number of factors such as size-controlled synthesis and shape-controlled synthesis are more significant toward the synthesis of nanomaterials. From the fact that synthetic technologies are mainly classified into two types, top-down approach, you can see here, top-down, and bottom-up approach. Top-down approach is the process of slicing or cutting of a bulk matter with the intention to get small-sized nano-dimensional particles. Crushing, milling, or grinding are some of the methods in this approach. So we consider bulk matter and we can crush it into some nano-dimensional particles, for simple. It's a top-down. The other one, bottom-up approach, is the process of stacking of a material from its bottom stage, atom by atom, molecule by molecule, or cluster by cluster. Apart from these approaches, up to now, various synthetic methods are available for nanostructured advanced materials. There are special three types that are most important because of the importance of the process material. They are classified as physical, chemical, and biological methods. Controlled size, shape, perfect dimensionality, and prescribed structure are the main criteria for these kinds of new synthetic routes. So we choose these routes based on what we actually want to get, what our object or goal. We're talking about nanotechnology in different fields of knowledge. But we usually take our knowledge just simply observing the nature. Nature can give us lots of information about what's going on and what we can apply in engineering of new materials and so on and so forth. One of these effects is called the lotus effect, which refers to self-cleaning properties that are a result of ultra hydrophobicity as exhibited by the leaves of some sort of lotus. It's not only about lotus. There are a few plants that have this effect. Dirt particles are picked up by water droplets due to the micro and nanoscopic architecture on the surface. So you can see here. This minimizes the droplets adhesion to the surface, and if it's highly hydrophobic, and these self-cleaning properties allow to get all this dirt and take away. And not, as I said, it can be found in other plants, not only lotus. So dot particle with an extremely reduced contact area are picked up by water and then cleaned off the surface. If a water droplet rolls across such a contaminated surface, the adhesion between the dot particle and the droplets is higher than between the particle and the surface. This cleaning effect has been demonstrated in common materials such as stainless steel when this highly hydrophobic surface is produced. Also, the self-cleaning phenomenon of the lotus was possibly known as in Asia long before this explanation of nanotechnology. Its mechanism was explained only in the 1970s after the introduction of the scanning electron microscopy. And based on this concept, nanotechnology uses in some industrial and everyday life, as you can see here. So we applied something that we see in nature. Another effect is called gecko effect. So geckos have a largest mass and then develop the most complex hairy attachment structures among living animals. And they're capable of some smart adhesion, the ability to cling to different smooth and rough surfaces and detach at will. So they use this specific hair to create this adhesion. So these animals make use of about 3 million microscale hairs that branch off into nanoscale spatula. About 3 billion of these spatula on the feet. So high area, so many of them. And this it provides the very high dry adhesion. So multiple level hierarchically structured surface construction provides the gecko with the compliance and adaptivity to create a large real area of contact with a variety of surfaces. So you may see here in the picture how it actually look like and the scanning electron image of these hairs. You can see so many of them, so high area, and this actually the nanotechnological application in nature. What about the modern application of nanomaterials? We consider it a few applications of quantum dots, but generally nanomaterials a wide range of application, extremely wide range, and it continue to widen every day. It is very good analogy, the spheres with increasing diameter. So because it demonstrates nonlinear change in application option, like sphere surface area increases non-linearly with diameter growth. So this is the analogy, growth of diameter non-linearly increases the surface area. So the most remarkable spheres of new material application are the medicine and biotechnology, fabrication of materials with special properties, new materials for energy producing and storage. Nanotechnology is fueling a revolution in manufacturing and production, creating new materials used in a variety of different fields that you can see here. This is only some of these applications. It can be cosmetic, pharmaceutical, energy, catalytic materials, some environmental applications. Due to the great potential of this technology, there has been a worldwide increase in nanotechnology research investment. The use of nanotechnologies and nanostructured materials is increasing in construction and architecture. Innovative products are constantly being marketed in the building material industry, which are more durable, extremely lightweight, and they have high insulating properties. In addition, new building materials and techniques are also seen in coating with different properties to reinforce concrete, glass, wood, brick, and metal surface coating. They're widely used in like nanotextiles. So like even it can be used in like nano socks and antibacterial, dirt-proof, iron-free, wrinkle-free pants, curtains, carpets, and many textile products, which are among the most common nano products of today. So new products are constantly being released. It's even very hard to follow all these changes today. Various improvements and developments in the sport equipment and tools used in almost every branch of sport can make a difference in uh, the competition, sport competition. With the development of high nutritional value and delicious products based on demand, desired products can be produced with thousands of nanocapsules to taste, colors, and some vitamins in their contents. So you can see there's a large scale of application. Some of them we can consider this. One of these is like automotive. So steel is the most important structural material used in vehicles, in vehicle bodies, I mean. The use of high strength steel in vehicles is being studied for a long period of time. However, in the cold forming of the steel, there are deviations in the dimensioning of the vehicle body. But this can be remedied by nanotechnology and multifunctional coating on the surface. So bonded and nano-sized glassy and plastic-like material together with aluminium form a strong layer on the surface. With the help of nanotechnology, scratch-resistant, non-polluting, and self-healing automotive uh, like parts can be applied to the exterior surface of the vehicle, of the car. Nanomaterials in vehicles make them more environmentally friendly and also improve the performance of automotive parts. Another is energy application. Well studied, and it still continues to modify the energy devices. So, and nanotechnologies have great potential for cleaner, more efficient, and environmentally friendly energy generation. Energy-related technologies where nanotechnologies can play important roles are lighting, heating, transport, renewable energy, energy storage, sorry, fuel cells, hydrogen production, and storage of hydrogen storage. So using nanotechnology to manufacture batteries offers some benefits, like increasing the available power from a battery and decreasing the time required to recharge a battery. This is pretty important in today's life. These benefits are achieved by coating the surface of an electrode with nanoparticles, increasing the surface area of the electrode, thereby allowing more current to flow between the electrode and the chemicals inside the batteries. Nanomaterials can be used as a coating to separate the electrodes from any liquids in the battery. Then the battery is not in use. In the current battery technology, the liquids and solids interact, causing a low level discharge. This decreases the shelf life of a battery. The nanotechnology also has some challenges in batteries. So even though they provide more like um, the longer lifetime and whatever, but they have low density and high surface area. The greater the surface area, the more likely reaction to occur on the surface with the air, which is pretty dangerous for the batteries. This serves to destabilize the materials in the battery. Owing to nanoparticles' low density, a high interparticle resistance exists, decreasing the electrical conductivity of the material. So nanomaterials can be difficult to manufacture, increasing their cost. While nanomaterials may greatly improve the ability of a battery, they may be cost prohibitive to make. Another is environmental use. So nanosensors play an a vital role in monitoring the ecological quality of air, water. Various nanostructured materials have been developed for the detection of different components. Environmental cleaning, or sometimes it's called remediation, consists of works that are free from chemical and radiological contaminants and do not endanger human health. For example, aerogels. They're a class of synthetic porous ultralight materials derived from a gel in which the liquid component is replaced with gas. So liquid component, and now we have gas without significant collapse of the gel structure. The result is a solid with extremely low density and extremely low thermal conductivity. They can be made from a variety of chemical compounds. Also in defense technology, can be war uniforms with the following characteristic and qualities with nanotechnological development that can meet the requirements expected from uniforms and combat clothing and camouflage nets, different covers, and they have been developed. Defense tools are becoming areas where nanotechnologies are used in every aspect as advanced technology platforms all over the world in an extremely diverse and wide range. So defense tools, and you may see in picture, in which different nanotechnologies are applied are especially stand out with their stealth features. But as for me, the most fascinating is the use of nanotechnologies in medicine and drug delivery. The drug development process is a complex, cost-effective, time-consuming process, and failure of a drug candidate takes place as a result of a number of limitations, such as poor pharmacokinetic profile, lack of efficiency, especially side effects, fluctuations in plasma drug levels. Nanotechnology plays a vital role for the development of materials by controlling their shape and size at the nanometer scale to improve physical, chemical, pharmacological, like pharmacokinetic, pharmacodynamics, to treat various diseases such as obesity, diabetes mellitus, malaria, cardiovascular diseases, leukemia, cancer, Alzheimer's diseases, and so on and so forth. The surface properties of nanoparticles, such as surface charge, hydrophobic nature, functional groups, are key factors for their biological activity. This technology is potentially applied at the cellular level of disease state in human beings with a high degree of specificity and also to achieve the utmost therapeutic efficiency with fewer side effects. So nanoparticles are actually, you can see the size of this smaller than bacteria, 1 nanometer. I mean, so the nanoparticles will be the size of genes, bacteria, and so on and so forth. So these we have two categories of these nanoparticles. It can be organic and inorganic. So you can see in the picture some examples of them. So organic are dendrimers, micelles, liposomes, whereas gold nanoparticles, quantum dots, superparamagnetic ion oxide nanoparticles are called inorganic nanoparticles. So both organic and inorganic are used in nanomedicine and drug delivery. The most promising application of nanomaterials is the target site-specific drug delivery. The potential of eliminating a tumorous outgrowth without any collateral damage through nanomaterial-based drug delivery has created significant interest. You know that now traditional treatment for cancer tumors make such a great and dangerous side effects and make impact on all body. But these targets can minimize all of these effects of this and make it more comfortable for the patient and can we make it more efficient at the end. So modifying or functionalizing nanoparticles to deliver drug through the blood-brain barrier for targeting the brain tumors can be regarded as brilliant outcome of this technology. Gold nanoparticles are generally produced by reducing chloroauric acid, you can see there. And you may ask, why gold? Actually, people usually like gold as some jewelry or coins and whatever, because gold is inert. But from chemical point of view, gold is pretty boring. As it's inert, it's absolutely not interesting. But when we go to the nanoscale level, gold becomes more and more interesting, especially in medicine. It's inert, so it does not interact with any other molecules in human body. But using, for example, sulfur atoms in covalent bond, we can attach the drug to this nanoparticle and it can be delivered. So gold nanoparticles have good biological compatibility due to their also optical properties like fluorescence, chemiluminescence. Gold nanoparticles are used as biomarkers for the detection of various biomolecules. So we can see it's kind of on detector in different lights, like some light markers. These nanoparticles provide a microscopic probe for the diagnosis of cancer and heart diseases. It's found that the gold nanoparticles are well absorbed in soft tumor tissues and making the tumor uh, sensitive to the radiation. So you can see it's that what Richard Feynman proposed as the swallowing the doctor. Is that what we see now? So there are many applications, especially in gold nanoparticles, like therapeutic drug delivery, antibiotics, and antifungal activity, etc. And future cancer treatment might use gold nanoshells to fight tumors. Gold nanoshells are tiny spheres of glass covered with a thin layer of gold. In an experimental treatment, gold nanoshells are injected into the body and collect in the tumor. Near-infrared light is then shined on the tumor. The light passes safely through the healthy tissue, but hits the gold nanoshells and destroys the tumor. Pilot studies indicate that the treatment is successful with minimal side effects. So gold nanoparticles materialize as promising carriers of biomolecules like protein, peptides, nucleic acid, drug molecules, etc. There are low inherent toxicity and multifunctionality, high surface area, photophysical and optical properties, impart unique attributes that have a great importance in chemotherapy, cancer diagnosis, bacterial diagnosis, and drug delivery. An important issue that needs to be addressed is the engineering of the particle surface for optimizing properties such as bioavailability and non-immunogenicity for the use of gold nanoparticles in various biomedical applications. On the other hand, it is early days in this field and still need to be explored. So to find more about nanomaterials, we have to study the newest articles which appear day from every day, and we have new and new information about the application. So when we summarize, we can make some conclusion about the dimensional properties, about quantum and classical characteristic of nanoparticles, and about their application, all based on the quantum mechanics and the quantum confinement and so on and so forth. So here we can see some links and references you can use to find a bit more. It's only a few pretty interesting articles to find about nanomaterials and the newest nanotechnologies. Thank you for your attention. My lecture is over, and I hope you found it interesting.
First of all, the basic of general physics and quantum mechanics, as well as the basic of chemistry. Carbon as an element was discovered in 18th century from charcoal and got its name because carbo means coal in Latin. Carbon is fourth most abundant element in our solar system, and it is 17th in Earth's crust. After oxygen, carbon is second abundant element in the human body. It is very interesting that carbon is sixth element in periodic table and sixth most abundant element in the universe. Carbon is unique because of its 4 valence electrons, which makes it very versatile and allows it to bond with many other elements. There are over 10 million no-carbon contains compounds, organic and inorganic. As you know, the main reason for electrical, optical, magnetic, and other properties of materials is features of its electronic structure. Here is a short timeline containing information about the year of discovery and the main hours of work related to carbon nanostructures. Among the new materials developed with the advancement of nanotechnology, carbon nanomaterials should be highlighted because they are considered highly versatile. Carbon nanomaterials presented thermal, electrical, chemical, and mechanical characteristics, besides the richness and diversity of carbon, which is the chemical element that considers the symbol of life. The discovery of fullerenes, followed by carbon nanotubes, and the recent isolation and characterization of graphene in 2004 provided new possibilities in chemistry and physics of carbon and increased interest in carbon nanomaterials. Due to its electronic structure, carbon forms a number of allotropic modifications. Allotropy is the properties of some chemical elements to exist in two or more different forms, now as allotropes. Allotropes have different structure. The atoms of the same element are bonded together in different manners. As a result, the different allotropes have different types of symmetry of crystal lattice. The allotropes of carbon include diamond. The carbon atoms are bonded together to form a cubic lattice or tetrahedron. Graphite. The carbon atoms are bonded together in sheets of hexagon lattice. Graphene, single sheet of graphite. Fullerenes, the carbon atoms are bonded together in spherical, tubular, or ellipsoidal formations. Carbon nanotubes, Q-carbon, carbene, amorphous carbon, cyclocarbon, glassy carbon. Each allotrope has the spatial properties, but what is the reason of structure variation and the crucial change in properties of different allotropes? As you know, carbon atom consists of 6 protons, 6 neutrons, surrounded by 6 electrons. We remember that the Rutherford model of an atom where the electrons are like the planets of solar system is only the basic one. But at the next level, we should use term of quantum mechanics about the electron as a wave packet distributed over certain orbitals. The electronic configuration of carbon is 1s2, 2s2, 2p2. The 1s orbital is the lowest energy level. Since 1s can only hold 2 electrons, the next 2 electrons go into s orbital, and it can also hold a maximum of 2 electrons. The 2p orbitals is the third energy level, and it consists of 3 sublevels. 2px, 2py, and 2pz. Each of these sublevels can hold a maximum on 2 electrons. In carbon atom, 2 of the 2p orbitals, 2px and 2py, hold 1 electron each, while the third 2p orbital, 2pz, is empty. The electronic structure of carbon accounts for the ability of carbon to form 4 covalent bonds, as it can share its 4 valence electrons with other atoms to achieve a stable electronic configuration. What is the excited state of atom? It is a state in which the total energy of electron can be lowered by transferring one or more electrons to different orbital, which the higher in energy. The next step of energy optimization of carbon atom as a quantum system is an orbital hybridization. Hybridization is a concept that describes the mixing of atom orbitals to form hybrid orbitals with different geometrics and energies. This hybridization occurs when atoms bond together to form a more energy efficient configuration. So, the hybridization predicts the certain symmetry of atomic spatial distribution. There are 3 options of hybridization of 2s and 2p orbitals, which are known as sp, sp2, and sp3, and corresponding to formation of 2, 3, or 4 hybridized orbitals. Each hybridized orbital has spatial geometry like a symmetrical dumbbell. Each sp3 hybridized orbital has an electron, and the electrons repel each other. To minimize repulsion between electrons, 4 sp3 hybridized orbitals are arranged around the carbon nucleus so that they are as far away as possible from each other, resulting in the tetrahedral arrangement of 4 sp3 hybridized orbitals around the carbon nucleus. To minimize repulsion between electrons, 3 sp2 hybridized orbitals are arranged around the carbon nucleus so they are as far away as possible, resulting in their planar trigonal arrangement. The 2p orbitals that did not take part in hybridized has 1 electron. Again, to minimize the repulsion between electrons, it positions itself to be as far away from each sp2 hybridized orbital as possible, which resulting in the 2p orbital perpendicular to each sp2 hybridized orbital. To minimize repulsion between electrons, 2 sp hybridized orbitals are arranged around the carbon nucleus to be as far away as possible, resulting in their linear arrangement. 2 2p orbitals that do not take part in hybridized and are perpendicular to each other have 1 electron each. Again, to minimize repulsion between electrons, they are arranged to be as far away from each sp hybridized orbital as possible. So, now we understand the reason for different types of crystal symmetry formation. And this reason is energy optimization of the system, where major components in electrostatic energy. At the same time, we must consider the other component of energy of the system, energy of unsatisfied chemical bonds and surface energy. Finding the balance between this kind of total energy under different conditions, temperature or pressure, causes nucleation and growth of nuclei with different crystal structure. The most stable form of crystal order carbon are graphite and diamond. but the different geometry of the hybridized orbitals can result in linear, one-dimensional, planar, two-dimensional, or tetrahedral, three-dimensional spatial organization of crystal and amorphous allotropes of carbon. Graphite and diamond correspond to sp2 and sp3 hybridized, respectively, but finding the balance between components of energy can lead to formation of more complex forms like fullerenes or nanotubes. In some cases, the formation of amorphous form of carbon with mixed type of hybridization is more beneficial. So, the phase diagram of carbon that composed of only 4 phase regions is only approximated. The reality is more complicated. Let's make a brief overview of some most important carbon allotropes. Let's start with diamond. As you know, diamond has tetrahedral arrangement of atoms corresponding to sp3 hybridized. As a result, we obtain the density form of carbon in which corresponding all valence electrons are involved in bond formation. So there is no lone pair of electrons. Due to this, diamond has a very low electrical conductivity as well as a wide band gap. It is transparent for visual range of light spectrum and is insoluble in all solvents. It is unexpected, but these properties, optical and chemical, have the same reason, characteristic of electron structure. Diamond is a harsh natural substance. It was a quite high melting point, but is flammable and can be oxidized directly into carbon dioxide. Diamond can be burned without residue. Diamond has a very high refractive index and it is a good heat conductor. It is a result of electronic structure too. The next one is graphite, a black or dark gray color with metallic luster. It consists of the same atoms, but its properties differ from diamond. As you know, the light absorbs is a result of photon capture by an electron, and transparent bodies have high energy of excitation of valence electron and, as a result, low concentration of free electrons. So, the metal foil is not transparent because excitation energy of valence electrons for metal is very low, which causes good electric conductivity. Black color and metallic luster of graphite are the manifestation of high density of free electrons. Really, each carbon if graphite is sp2 hybridized. Thus, one valence electron of each carbon atom is free to move from one point to another. The unhybridized orbital containing one electron each overlap laterally to form bonds in the same layer. These free electrons are delocalized and move under the interfluence of heat and electric field. Thus, it makes a good thermal and electric conductor. Graphite has lower density compared to diamond due to large distance between the layers. The sp2 hybridized type of carbon atom leads to planar structure of graphite crystal lattice when the carbon that form the individual layers are strongly covalently bonded, when the separate layers are respectively weakly bonded. Due to this characteristic, You can produce carbon nanomaterials directly using only paper and pencil. When you write with a pencil on a paper, the plain fragments of graphite crystals are exfoliated, and line grown on the paper consist of a series of carbon nanoparticles. The pencil rod is a polycrystal, but it doesn't change the case. The same graphene was first used in 1962 when this material was actually observed for the first time the German chemists Ulrich Hoffmann and Hans Pieper Boehm, who named it graphene because it's a graphite junction with the suffix "in" related to the double bonds existing. However, it was only 4 decades later when graphene was isolated and first characterized by researcher Game and Novoselo of the University of Manchester through the technical exfoliation of graphene sheets in individual layers or small plates of pyrolytic graphite. Novoselo, Game and co-workers improved the efficiency of the materials, improved its conductivity, and setting it to the thickness of an atom. To the researcher's surprise, the ultrafine materials present not only a structure as flat monolayers of carbon atom connected hexagonally, but also excellent thermal and electrical conductivity, good mechanical resistance, being light, flexible, and presenting a large specific surface area. What are graphene advantage over graphite? Strengths, flexibility, electrical conductivity, exceptional optical properties have opened new horizons for high-energy particles physics research and electronic, optical, and energy applications. In graphene, each carbon atom is covalently bonded to 3 other carbon atoms. Due to the strength of the covalent bonds, graphene has great stability and very high tensile strength. What is the difference between graphite and graphene? Firstly, about graphene properties. Graphene is transparent with a thickness of about 1/3 of nanometers. It absorbs only 1/15 of incident light. Graphene has an extremely low electrical resistivity that corresponds to highest electron mobility of conductors. As a result, this material has exceptionally high thermal conductivity. The characteristic of crystal and electronic structure causes the unique mechanical properties. For example, monolayer graphene is the strongest materials ever tested, more than 100 times stronger than the strongest steel. Graphene has very high surface area. Theoretical limit is more than 2,600 square meter per gram. So 3 grams of graphene is the size of a football field. There are 2 types of electron in solid carbon. Electrons in the s and p shells associated with the atom. The energy of all electrons is quantized. According to Pauli principle, only 2 electrons with opposite spin can have the same energy in the same quantum system. For example, graphene particles. When a system consists of many identical atoms, the individual energy levels of the electrons of individual atoms turn into energy bands. The energy of electrons depends on the lattice. The spatial distribution of atoms is the reason for a certain symmetry in the intracrystalline electric fields, which determines the allowed energy state of electrons. The grouping of these different energy levels for free and bond electrons form energy bands. Valence bands consist of energy levels of valence electrons. Conduction band consists of energy levels of free electrons. Forbidden energy gap is the energy gap between the valence band and the conduction band. The valence band and conduction band overlap in the case of a conductor. There is a small band gap between the valence band and the conduction band in the case of semiconductors. Between the valence band and the conduction band in the case of insulation, there is a large band gap. As you know, the quasi-momentum of electron in crystal is proportional to its wave vector. So, for the approach of quasi-free electrons, its kinetic energy is described as, and it means that kinetic energy is proportional to squared quasi-momentum or square k vector. Corresponding that we should use all three components of k vector, kx, ky, and kz. We can predict that the dependence of energy of electrons on its k vector for each of its components has a paraboloid shape. We remember that these dependencies aren't continuous but consist of the separate change, each of which correspond to individual cell of K space, which can contain two electrons with opposite spins only. We remember that the absorption of emission of electromagnetic waves occurs of electron transition between cells belonging to conduction and valence band. We remember that the highest probability was transition without changing k vector. This energy range corresponds of optical band gap. The width of the band gap determines the class of materials, conductor, semiconductor, or insulation. So, where is graphene in this list? Graphene has a special electronic structure. Each atom in a graphene sheet is connected to three nearest atoms by sigma bonds and delocalized pi bonds, which contributed to the formation of a valence band that spans the entire sheet. The valence band touches the conduction band, making graphene a semi-metal with unusual electronic properties that are best described by massless relativistic particle theories. Change carriers in graphene show a linear, not a quadratic dependence of energy of on momentum. But there is another factor, quantum confinement. Quantum confinement effect is a restriction of the movement of an electron in the materials to specific discrete energy level rather than to quasi-continuum of energy band when the length of the particles is reduced to the same order as the wave packet. The difference in energy between field states and the empty states depends on the size of graphene particles, so the band gap can be turned. The electronic properties of graphene change with the number of layers and with the relative position of atoms in adjacent layers determined by the order of stacking. Therefore, graphene should not be considered as a single materials, but as a family of compounds that can be formed by a single layer of atoms, monoatomic sheets. Two materials formed by two, 3, 4, etc. Graphene sheets are stacked in an organized way. Thus, the electronic structure of the graphene presents different coupling with the increase in the number of layers up to limit of 10, 20 layers when the materials in consider graphite. It is very important that graphene sheets, single and multi-layer, are the building blocks for other graphitic materials. When we roll up graphene, we can obtain the carbon nanotube. After cutting and folding the graphene sheets, we can obtain closed system formed by carbon atoms, fullerenes, and the properties of nanotubes and fullerenes as spatial and size sensitive. Let's consider the method for obtaining graphene. Mechanical exfoliation is the method that allowed the isolation of graphene for the first time and is used until today. It is in this method an adhesive type is used repelled to perform exfoliation of high purity graphite. Next, some capture flakes are transparent to the surface of the silicon or silicon oxide disc, and it is possible to verify the existence of graphene by an atomic microscopy. This approach presents good reliability and provides graphene samples that are practically free of defects. However, the main problem is that it does not allow the production of graphene on large scale. Another method is chemical vapor deposition. This method is based on the thermal decomposition of carbon-rich gas with deposition of carbon atoms of the metallic catalytic support. The Honeycomb arrangement of carbon atoms is formed because it is energy friendly. So, this method is complicated and expensive, but allows up to produce good quality graphene films with large surface area. The advantage of this method is stability. Meanwhile, what is price of graphene? Graphene costs less than $0.1 per gram. This can be very profitable with gold price at around $60–65 per gram. The next one is chemical exfoliation method, which allows the graphene synthesis in dispersion from graphite using stage of intercalation, exfoliation, and sonification. The main advantage of this method is low price of its production. This method is very close to graphene oxide route. What is graphene oxide? These are graphene-based compounds that contain epoxy, hydroxyl, and carbonyl groups on the basal plane and carboxyl groups on the edges. What are properties of graphene oxide compared to graphene? A higher interplanar spacing than graphene due to sp3 carbons, a higher ability to retain compounds, lower electron mobility compared to graphene, solubility in water, versatility. It is able to interact with biological cell and tissues, a highly hydrophilic, substance deposition capability, convertible into a conductor. The main advantages of graphene oxide are hydrophility and biocompatibility in contrast to graphene. I have an experience to deal with graphene nanosheets, and it's very complicated due to its hydrophilic nature. Graphene oxide is cheap polyfunctional materials, soluble in water and bio-friendly. Another important property of graphene oxide is substrate deposition capability and the possibility of sensitive tuning of band gap. The graphene oxide synthesis route is based on the sulfur ions intercalation between the layer form of graphite crystal with the following oxidation, sonification, and resulting exfoliation. So we finally obtain this light yellow-brown colloidal solution that contain individual fragments of multi-layer graphene oxide particles. This slide shows the synthesis route evolution film by my students, which lead to obtain graphene oxide. The most common method of structure properties testing is X-ray diffraction, where the atoms of solid became 3D diffractive lattice. Using this method, we can trace the evolution of structural transformation from initial graphite to graphene oxide by the analysis of the presence of characteristic peaks. Using this method, we also can estimate the average size of graphene oxide particles. According to the calculation, typical graphene oxide particles is our experiment have lateral size along graphene plane of about 10 nanometers, when the average thickness is about 1 nanometer. So you already understand what is the main problem with the graphene oxide. Graphene oxide is highly defective material. Chemical exfoliation or chemical reduction involves the conversion of graphite to graphene by the introduction of functional groups containing oxygen by reacting graphite with strong oxidized agents such as sulfuric acid or nitric acid. This reaction forms graphite oxide, which is chemically reduced to graphene using reducing compounds such as hydrogen or sodium borohydroxide. The chemical exfoliation from graphite to graphene is possible because is the addition of groups such as OH and COOH that by chemical oxidation reduce van der Waals forces. Responsibility for keeping the graphene sheets in the structure of the graphite and the separation takes place. The main advantage of this method is the possibility of obtaining graphene with good uniformity and excellent yield. When compared to the mechanical methods, allow is used to obtain graphene or a large scale. Reduction of graphene oxide allows us to obtain graphene-like materials, which is very cheap but with loss of structural defects. Reduced graphene oxide is a form of graphene oxide that is produced by chemical, thermal, and other methods in order to reduce the oxygen content, while graphite oxide is a material produce the oxidation of graphite, which leads to increase interlayer spacing and functionalization of the basal plane of graphite. One of the most important difference between graphite oxide and reduced graphite oxide is the electrical conductivity of these materials. While graphene oxide show insulation of semiconductor behavior, reduced graphene oxide show excellent electrical conductivity, which is more good as graphene. The main disadvantage of the reduced graphene oxide is defect structure. We can observe this defect using transmission electron microscopy. As you remember, the rolling up the graphene nanosheets allows up to obtain nanotubes with the diameter of 1 nanometer for single wall structure with the length from nanometers to several microns. It is very important that nanotubes can be metallic or semiconductor depending of their geometry. Today, the term carbon nanotubes corresponding to a family of compounds that may have different characteristics from each other. Carbon nanotubes can be divided into two groups, single-wall and multi-wall carbon nanotubes. Single-wall carbon nanotubes emit up only one sheet of graphene and have a diameter for 1 to 5 nanometers. However, the synthesis method currently used to produce only a small fraction, and single-wall carbon nanotubes increase in cost and make it difficult to be applied on the large scale. Multi-wall carbon nanotubes form but a set of two or more concentrically rolled graphene sheets, which may have diameter of 10, 15 nanometers. So, not only size, but also geometry matters. There are different options for rolling up graphene nanosheets for formation of nanotubes, which depend on the direction of the axis of the tube related to the honeycomb cells of carbon atoms that form graphene sheets. Each carbon nanotube is characterized by chiral vector, which defines zigzag and armature option, as well as intermediate chiral option. Depending on the way the graphene sheets wraps around, carbon nanotubes may have different geometrics and properties. In this way, the electrical properties of the carbon nanotubes depend on how the hexagon are oriented along the axis on the tube. Depending on their diameter and chirality, carbon nanotubes may be easy semiconductor or semi-metallic. For example, the armature structure behaves as a metallic materials, whereas the zigzag structure has semiconductor or quasi-metallic properties. What leads to the formation of carbon nanotubes? Nanotubes Fullerene combines sp2 plus sp3 hybridized carbon atoms. Finite size of graphene layers has dangling bonds as unsatisfied balance of immobilized atoms. This dangling bond corresponding to high energy states. Both the elimination of dancing bonds and an increase in the strength energy leads to a decrease in the total energy. There are band structure of carbon nanotubes in comparison with band structure of free electrons and graphene. Changing the type of geometry, zigzag, chiral, armature, makes it possible to tune the carbon nanotubes band structure from metallic to semiconductor. So, let's sum it up. We have chemically stable quantum size unit with the tunable electronic and as a result, electric properties. Carbon nanotubes have several attractive and promising properties for various applications because of their structure. The strength of the sp2 bonds gives carbon nanotubes high chemical and mechanical resistance. However, even presenting one of the most robust structure now, this material has high flexibility and can be bent without destroying its structure. In addition, carbon nanotubes have a higher tensile strength than steel and excellent thermal and electrical conductivity. Carbon nanotubes have the extremely high mechanical strength properties, one order of magnitude compared to titanium, very high thermal conductivity, high electrical conductivity, 6th order of magnitude higher than copper. Carbon nanotubes are the best materials for the components for the electronics. The application range can be wider using the functionalization technique. What are the methods for nanotube synthesis? The electric arc discharge is a very simple approach, as you may see. It is based on the graphite electrode burning in the inert gas atmosphere under the applied electric field with the possible catalytic support. A potential of 20-25 volts is applied across the pure graphite electrode separated by 1 micrometer distance and maintained at 66.7 kilopascal pressure of flowing helium gas filled inside the quartz chamber. When the electrodes are made to strike each other under this condition, it produces an electric arc. The energy produced in the arc is transparent to the anode with ionize the carbon atoms of pure graphite anode and produce C+ ions, and plasma forms atoms or molecules in vapor state at high temperature. These positively charged carbon ions move towards cathode, get reduced and deposition and grow as carbon nanotubes on the cathode. As the carbon nanotubes grow, the length of the anode decreases, but the electrodes always have a gap of 1 micrometer between the two electrodes. Another method is chemical vapor deposition. The chemical vapor deposition method is to cleave a carbon atom containing gas continuous flowing through the catalyst nanoparticles to generate carbon atoms and the generate carbon nanotubes on the surface of the catalyst or the substrate. The final step of geometry optimization of carbon nanostructure is the fullerenes formation. Unlike the other allotropes, the fullerenes are in molecular form and consider spherical nanometric molecules formed only with carbon atoms. Since 1966, theoretical calculation demonstrates the possibility of the extension of cage formed only by carbon atoms. However, only in 1985, the existence of fullerenes was provided in the work of Harold Kroto, Robert Karl, and Richard Smalley. With the help of Karl and Smolny, Kroto performed an experiment in which a graphite plate was subjected to a pulsar high-frequency laser forming agglomerates, which were later analyzed by mass spectroscopy. At the end, in this experiment, the formation of molecules with 60 carbon atoms was observed, leading researchers to search for molecular structure that gives stability to these molecules. Kroto had the idea of organizing the atoms of the same form of the georetic domes by the architect Richard Buckminster Fuller, in which hexagonal face construct a spherical structure due to combine with pentagons. In this way, the structure of the C60 was defined as a polyhedron of 32 faces, 20 hexagonal and 12 pentagonal, and was called Buckminster Fullerene in honor of the American architect. Each carbon atom is bonded to three other and is sp2 hybridized. The C60 molecule has two bond lengths. 6 to 6 ring bonds can be considered double bonds and are shorter than the 6 to 5 bonds. The geometry and electronic bonding factors in the structure determine the stability of the molecule. Among physical properties, we can admit very high resistance and extremely high biochemical stability. Other stable forms of fullerene were already isolated as, for example, C20, C70, C78, and C84. However, in all these forms, C60 fullerene is the most abundant and most stable, with pi bond between the 6-member rings and single bonds between the 5-member rings. We should understand that the ideal hexagonal and pentagons in fullerene structure are only part of a model. These fullerenes are deformed and have structural defects. In all the studies that were already done on fullerenes, one of the interesting discovery in the ability of C60 molecule to receive from 1 to 6 electrons. Even so, it is already rich in electrons, forming corresponding anions. Other properties of fullerenes are good chemical stability, large surface area, high mechanical resistance, and the ability to become superconductor when combined with alkali metals. These properties make these materials promise to several types of applications, such as photovoltaic, biomedical application, transport of antibiotics, and the development of sensors. The synthesis route of fullerenes is very similar to obtain nanotubes. Electric arc process to produce fullerenes is based on the evaporation of graphite electrodes in a low-pressure helium atmosphere by passing an electrical current through the electrodes, resulting in arc that produce carbon black containing fullerenes. This method usually leads to the production of various fullerenes in various mixture and other form of carbon. So, the fullerenes are mainly extracted from the soot using approached organic solvents. At the synthesis, not individual fullerenes are obtained, but their aggregates. The reason is that the system reduces the excess surface energy with proportion to the surface area of the materials. The specific surface area can be very large to carbon nanomaterials. If in one-dimensional carbon structure, we reduce the length to nanometer size, we'll obtain nanocage. Fuller N is a perfectly spherical nanocage formed by a number of pentagonal and hexagonal rings. Carbon nanoonions are caged with spherical or polyhedral shape formed by several fullerenes-like overlapped carbon shells, which are defective and disordered to a certain degree. They were discovered in 1992 by Uran during electron beam radiation of an amorphous carbon sample using transmission electron microscopy. Another one-dimensional carbon nanotubes is represented by the carbon dots. Typically, the average dimension of carbon dots is about 5 nanometers. Quantum confinement effect provide excellent optical properties as highly top-night photoluminescent, high photostability. Carbon nanoonions remain as one of the most interesting carbon forms, along with graphene and its derivatives due to their unique chemical and physical properties. Their high biocompatibility and biosafety make them an attractive choice in a wide range of areas, including biological systems. These nanomaterials display low toxicity, high dispersity in water solution, and high pharmaceutical efficiency. Carbon nanoonions were discovered almost at the same time of carbon nanotubes, but their potential in biomedical application is unrealized. Carbon nanomaterials have a potential application in several systems, products, and devices such as electron emitter for televisions, in composites with polymers, ceramic and metals, diodes, transistors, photovoltaic devices, computer memories, and the development of electrical, chemical sensor and biosensors. Wilson report highlights the importance of carbon nanotubes to support bone growth by changing the mechanical properties of natural and synthetic polymers. The properties of carbon nanotubes are affected by their synthesis process. Carbon nanotubes can be used in the fields of a nanosensor for the detection of the pathogens and for water treatment. The unique properties of nanomaterials such as small size, large surface area, and reactivity provide good opportunities for its use in the agricultural sector. The application of carbon nanotubes in this field includes seed germination, early plants grown, and biosensor diagnostic and analysis. Among the different carbon allotropes, carbon nanotubes have attractive attention in transporting various drug molecules into the living cells. Due to their ability to conduct electricity about 100 times that of copper wires, carbon nanotubes are used to convert the electrical signal generated by target recognition. Their thermal conductivity is higher than diamond, and their strength approximately 100 times greater than steel. Last but not least, the ability of carbon nanotubes to grow biological membranes make them used in vivo with minimal invasion. Different classes of carbon nanotubes, the biosensor, have been developed to probe cancer biomarkers. Carbon nanotubes could potentially be used in prophylactic medicine for monitoring of fever or hyperthermia caused by special pathogens. Nanotechnology plays an important role in water treatment. Carbon nanotubes can be used for the wastewater treatment. Absorption and degradation is the key strategy for the removal of contaminated from the sample through carbon nanotubes. It is possible to target a spatial contaminant through the well-modified carbon nanotubes. Design or modification of carbon nanotubes properties may also assist in the separation of materials following the contaminant treatment process. Nanoparticle separation is simplified by incorporation of magnetic components into carbon nanotubes. It is easy to control the potential and the current in the electrochemical technique for wastewater treatment. Fullerenes are also used in several biomedical applications, including to the design of high-performance MRI contrast agents, X-ray imaging contrast agents, photodynamic therapy, and drug and gene delivery. Seasickness is used in drug delivery system and a catalyst. Some types of fullerenes can be used of gas absorption. Films based off fullerenes are used for photovoltaic application and hydrogen gas storage materials. Nanomaterials can be used biosensor to increase sensitive and lower defectant limits. A biosensor is a device that can measure the number of molecules in a solution containing analytes using their reactive properties with a specific substance. The physicochemical potential makes carbon nanomaterials an ideal materials for scientific application to detect the pathogens. In comparison with the commercial sensors, such as metal oxide of silicon, carbon nanotubes-based biosensors have significant advantages, such as highly sensitive, excellent luminescence properties, fast responding time, and high stability. This improved performance is due to the small size of nanomaterials, which gives them a large surface volume ratio. This high specific area allows immobilization of great concentration of bioreceptor, units related to biosensor surface volume. Several sensor and biosensors based on graphene-related materials, such as graphene oxide and reduced graphene oxide, have been reported in recent years for the analysis of compounds from environment sources. Some example are the detector of metal ions such as lead and cadmium, food analysis, clinical applications such as in the detection of glucose and drugs. In addition, graphene can form composites with other materials such as polymers, nanoparticles, and biomolecules such as DNA by physical adsorption or chemical bonding. As a result, by combining the thermal, electrical, and mechanical properties of graphene with the properties and function of several other components, new materials and innovative analytical system can be created, providing the sustained progress or chemical analysis. Besides polyethylene, carbon nanomaterials can also be used to provide shielding from cosmic radiation. While pure graphite has better shielding properties than the often used aluminum, its mechanical properties are poor, resulting in the necessary to improvise them by additional materials with a higher atomic number. Polyethylene, as the low Z materials in the composite, should be at surface layers and interact firstly with the incident radiation. In this way, enable the building of multi-layer composite from polyethylene and graphite, which give better radiation shielding. As simulated with a particle transport simulation code, taking into account solar particles, cosmic rays, protons, and electrons along the high elliptical orbit. The last but not least, a few words about biochar. Biochar is obtained by burning organic materials in a controlled pyrolysis. It is eco-friendly polyfunctional nanomaterials with very wide range of application from adsorbent and catalysis to supercapacitors and hydrogen storage technique. Using the biochar in our lab, we produce the attractive microporous carbon. This carbon molecule contains pores with the size less than 2 nanometers. As a result, these materials have surface area in the range from 1,000 to 2,000 square meter per gram, when the theoretical limit is about 3,700 square meter per gram. We use two methods to preparate activated carbon using biochar as raw materials, physical and chemical activation. Porous carbon has extremely wide range of application, from medicine and industry to energy storage devices. Combination of very high surface area and good electric conductivity with chemical stability allow us to fabricate the electrochemical energy storage devices that bridge a gap between conversion In this slide, you may see a few photos that I took during research trips. Here is a periodic table in Griffith Observatory in Los Angeles, California, and carbon in a cell of the table. The risk in scanning electron microscope image of activate carbon and the Cambridge Graphene Center, the mission of which is to investigate the science and technology of graphene, carbon allotropes, layer crystal, and hybrid nanomaterials. To find more about carbon materials, you may use this reference. Thank you for attention.
Hello, everybody. So usually, like after the class, after the lunch, whenever I take a class, I usually take a demographic check. And how many of you are still awake after the lunch? Let's raise hand. Okay, so we got 1, 2, 3, 4, 5, 6 people awake. I think that's enough. Out of the 30 people, at least 6 people are awake. So okay. So we go with this 6 people. Okay. Remaining people, you can all chill or do whatever you want. Okay, so now another more important question for the presentation is like, how many of you know Python? How many of you are using Python? A programming language. You know? Little bit. Okay. Okay, so not many, but hopefully it will be rather intuitive. So what we'll try to do on this presentation is mostly focusing on what actually goes on inside a neural network. How many of you know what's a neural network? What's artificial intelligence? Have you heard about this? Anything? Good. So we try to understand how exactly some parts of the neural network works. And eventually, I will try to give you some example applications of neural network or artificial intelligence, AI in the nanotechnology. So personally, I study astrophysics, so I don't know much nanotechnology. So the presentation also is mostly dedicated towards deep learning, towards the understanding of the neural network, very little bit of nanotechnology. Okay, so let's begin. So I guess if you check the let me see. Okay, if you check the Reginna Summer School first one, so we had a image like this with this oranges, and that's also my background template. So you might ask, like, okay, so how did we get to these images? So this image was actually generated using an AI application. So yesterday, Egon came, I think Egon presented quantum computing with Qiskit and etc. So me and Egon, we were trying this with an application called DAL-E. So DAL-E is developed by OpenAI, same developers from the ChatGPT. So what you can do is, so Egon put this query in the search bar. So oranges arranged in a honeycomb pattern, and the computer generated, the application generated this very cool image. So this is a very advanced application of AI in image generation. To me personally, that's very, very fascinating. Of course, if we move on, what goes on in there is something like there's a big network that tries to learn from the text, then it converts the text into images. So there are billions of parameters in this network. What is a network? What is a parameter? We will come to this. But these are very complicated stuff. But the main part is, you can see here in this example that it generates a very realistic image. You put in a corgi, a dog, playing a flame-throwing trumpet. That's a cool image that the network generated. That's, to me, it's very fascinating. When I was like just getting started with AI, I never imagined that I could see some days like this. You put in a prompt and then it generates so realistic images like this. So this image is directly from the paper. If you're interested, that's the reference, this clip paper. Anyway, more than that, I think if you are in bachelor's level, you probably should be using ChatGPT. How many of you are using ChatGPT for your homework and etc.? Good. You should learn to use it, but you should also learn to be able to distinguish the right from the wrong. So ChatGPT is also a very, very advanced neural network. So the way it works is like, it's based on a language model, and you have a feed of text. So let's say I am going to present today at what ChatGPT does, what the network does is tries to predict what could be the next war at a school, at a university, or something, etc., etc. So it tries to come up with the most probable answer. So that's what it does. But a lot of things goes inside it. And the probabilistic model is given by something like this. If you know bachelor's physics or chemistry, what this calls is like a conditional probability. So what you see on the right-hand side, this x1, x2, x3. So this would be the words. I am going to present today at, then this xt plus 1, maybe at the university. So this is what the network is trying to predict. Again, developed by same developers from the DAL-E. So these are very advanced examples. Some other examples, I'm a big fan of music, playing music, etc. So Google also developed a music AI that can generate music automatically. So you can check this. There's a website called Music AI. So you can go there and you can write a punk rock mixed with living scale and etc. And then it will generate a music. Very fascinating. You just write the text and it generates music. Something similar as you write the text and it generates images. There are some other very advanced applications that are going on, which are not discussed so often. Like you see the applications of ChatGPT, you see the applications of DALL-E, but some other applications that I thought would be very interesting for you would be something like, at some point we need to discuss when an AI algorithm can get a model. Is there a possibility? So we are kind of reaching towards that stage. There are some amazing applications that are going on, and one of these applications is this. And we predict from the one-dimensional structures of the proteins, A, C, T, G, etc., can we actually predict how this protein would look like in 3D? This was a 100-year-long problem. It was solved last year by an AI. Fascinating stuff. So you give and 1D amino chain happens, the algorithm generates the 3D structure. The 3D structure is very important because with that 3D structure, you can actually predict whether this protein will be absorbed in your body with some particular chemicals or not, etc., etc. Fascinating task. It was published in Nature, one of the highest cited paper. Again, very, very cool applications of AI. Some other thing is on the application of nuclear fusion. So this particular thing is called the tokamak. Tokamak is a vacuum. It's a donut-shaped vacuum. So donut is like, you eat donut, so you know what a donut is. It's a vacuum, and inside the vacuum, what you have is plasma. So what you're trying to control is this plasma that stays inside this vacuum. It doesn't hit the wall of the chamber. This is controlled by controlling the magnetic fields of the coils. And this is a very, very complicated task because there are thousands of magnetic leads, and you need to change the voltages very fine-tuned so that this plasma doesn't touch the wall. If the plasma touches the wall, then there will be some energy loss, there will be some friction, etc., etc. And AI was actually deployed for this task in Switzerland, and it's very, very well performed this task. Fascinating. Another task that I found personally as a mathematician or physicist very important, very interesting is that it turned out that an AI can discover mathematical algorithms. Again, so if you're in bachelor's first or second year, you know matrix multiplication. We do matrix multiplication. The algorithm that we do now is existing for 150 years. It turned out that that algorithm is not one of the fastest algorithms. Again, a computer or an AI algorithm developed by itself a faster algorithm. And this is again published in Nature. So you see that these days there are tons of applications of AI. Whenever we say AI, you always have to think that it's some sort of a neural network. So we will try to understand what the hell is this neural network? What exactly is going on? So this is the primary part of this presentation. Hopefully you go back with some ideas what exactly is going on inside a neural network. By the way, this presentation is uploaded in the timetable. Also in the timetable, what you find is some Jupyter notebook. You run some small Python scripts, and you can check whatever I'm saying, it's kind of making sense or not. If you check by yourself, then I think it's always better. I will switch back to the presentation and the Jupyter notebook so that you can understand better. Okay, so if you like neural network, you will probably see some images like this. Some circular things arranged in a layer, and between the layer, we have this sort of connections. So there are some terminologies I will say again and again. So these terminologies would be the input layer, the first sort of bubbles where you input the data. What is data and etc. It will be more clear very soon. Just the kind of model. So the first layer is called the input layer. Then you have something called the hidden layer. The most of the calculations are going on in the hidden layers. And then on the final layer, we have the output. You will see what can be in the output, what sort of task we can do. Okay. So what exactly is now going on? So why it is called a neural network? So the analogy comes from the brain neuron. So what's going on is you can see a very nice example image. So this is from, if you type on Google, so Stanford has their whole computer vision course publicly available. So to me, again, this is very, very fascinating. I remember like about 10, 15 years back, I didn't have internet. So I had no access to this kind of stuff. But now I can just go to internet and I can access the whole Stanford course. To me, this is very, very fascinating, and you can learn a lot. So this image is from the particular example. So what you see here is that you have a neuron, some sort of connections that are flying through at the center of the nucleus, then it sends a signal through the axon. It's the same principle that's going on in a neural network. You get some connections, you get some numbers in, some sort of calculation going on here, and then it sends another signal. And that's the analogy between the neural network that's running in our brain, that's the real neural network. And that one we are trying to build in our computer is an artificial neural network. So the real one is in our brain. We are trying to emulate our brain as much as possible. Okay, so the first simple step that is going on in physics, it's called the linear operation. So if you know, I think probably from high school, equation of a straight line, something like y is equals to mx plus c, that's exactly the same thing that is going on here. So this w are called the weights. So these are just numbers. X's are the inputs, x1, x2, x3. So you multiply w with the x, you get an output. So this is a simple linear operation. But now we have to ask, okay, so we have a simple linear operation, but we want to do many complex tasks. Maybe we want to recognize an image. If it is the image of a cat or a dog or etc., how can a linear operation do this kind of complicated stuff? So linear operation cannot really do this complicated stuff. So what we do is we try to incorporate a nonlinearity. And this nonlinearity is called an activation function. So we try to figure out what would this nonlinear function be. So two of the biggest examples in the literature that you would find is something called, on the left, it's called the sigmoid function. And on the right, we have something called the tan H, the tan hyperbolic function. So what is going on here is that you give some input and the function tries to map into this value. Biggest advantage of this kind of activation function, for the left one, you can see from the graph that every value of the input is located between 0, or any value of input, the output is always located between 0 and 1. For the right one, every value of input, the output is located between -1 and +1. But it naturally incorporates the nonlinearity. So what is going on in the network? We have a linear operation, then we have this nonlinearity, then we have multiple nonlinearity because of many layers within, and we try to emulate complex nonlinear stuffs. This will be more clear very soon. By the way, so the one that we showed before, that one we actually don't use for current neural networks. What we use is something like this, a very simple activation function. So what it does, whatever the number you input, if it is negative, the output is always 0. If it is positive, it just predicts back the number. So in mathematics, we call this as this function, maximum of 0 and x. So we input, let's say, -2, then it will give me 0. If I put 3, then it will give me 3. And you can see for this part, whenever it is above zero, whenever the input number is above zero, it gives me a straight line because that's the equation of a straight line. Y is equals to x. So it's very simple. So now the next question is, can somebody tell me? So these are combinations of two linear functions. One is y is equals to 0, this one, and the other one is y is equals to x. So why this is a non-linear function? Does anyone know this? If you're studying mathematics or physics, can you tell me? How can we combine two linear functions and then it becomes a non-linear function? By the way, how many of you are studying physics or mathematics? Anyone studying physics or mathematics or no? You will study. Oh, any idea? So we have two inputs going on. Okay. So one is y is equal to 0. This line, right, becomes 0. The other one is y equals to x. So both are linear, right? So we try to join these two linear functions, and we say that this is a non-linear function. Why this is a non-linear function? This probably is discussed, I think, in about bachelor second or third year. Okay, if you don't know, huh? Take a guess. It's okay. I won't judge you.
Y equals 0
Okay.
and x equals 1.
Yes, y is equals to 0 whenever x is less than 0, and y is equals to x whenever x is greater than 0.
Y against the slower.
Let's write it back.
Let me write it down if you know.
Yes. So if x is less than 0,
Yeah.
then we have y is equals to 0. If x is greater than 0, we have y is equals to x.
And I have to see why it's not the linear function.
Yes. Why is that? Because y is equals to 0 is linear, y is equals to x is linear. So where is the non-linear?
Doesn't go lower than bottom.
No. Okay. Okay. So the answer is this is a discontinuous function, and the discontinuity is at 0. So if you open a mathematics book, this would be written as a piecewise continuous function. Piecewise continuous. For x less than 0, it's a continuous function. For x greater than 0, it's a continuous function. We try to combine this piecewise continuous function, and at y equals to 0, there is the discontinuity. And this creates the nonlinear function. It's usually asked if you are applying for an internship in a company for AI job and etc. Probably they will ask you. But anyway, for now, just take that this is a nonlinear function. It turned out that because the function is so simple, it just outputs the input whenever the number x is equals to 0. The training is very, very fast in a neural network. And there is a subtle problem in general training with this function. So let's say after finishing the studies, you join a bank. And you join a bank as a data scientist, and the bank give you some numbers. Okay, this customer is 40 years old. He has income about $40,000. He lives 100 meters away. You have to do some sort of classification, whether this customer will give you loan back or not. So the problem with this kind of data is you can already understand that, let's say, if you think about the age. So the age would be something like from 18 to 50. But if you go to the salary is something like 20,000 to 200,000. So there's a big, big gap between these two numbers. So the way we try to input these numbers in the neural network, we try to squeeze those numbers between 0 and 1. This is called the standard normalization technique. So whenever we are using this value, this sometimes called the value function, we will have to normalize the data. We will see an example. How can we do this? So what we are expecting? So I will mostly discuss on the presentation with images because that's what I deal with. And it's also, I think it's more visually appealing if I talk about images. So what we are trying to expect? So what you see in this image is one of the most preliminary tasks that was presented as a challenge for a neural network. You ask people to write from 0 to 9, many different people, many different times. And the neural network learns from the handwritten image what number the person has written, whether he or she has written 0 or 5 or 8, whatever. So what we are trying to expect is that a neural network learns the pattern of the data. So here is an example of what I mean by pattern, also on the next slide. So let's say if I take an image of a tree. So of course, the way I write 3, you don't write 3 like that. Somebody else will write 3 like that, or some other numbers. And this creates a massive problem. So let's say if I take my 3, and if I try to overlap with somebody else's 3, so let's say this one was my 3, and I try to overlap with one of your 3, this will appear different. But we recognize this very fast. Our brain is amazing. Okay, this is of course a 3. It doesn't matter if this part of the pixel is white or this part of the pixel is black, it doesn't matter. The brain recognizes very fast what is a 3, what is a 5. But how can we tell this to a computer that it is indeed a 3? And this is where comes the part of the patterns. What we expect is that the neural network learns some pattern in the data. So let's say here's an example of 9. What the way we try to think about 9 is maybe okay, maybe a circle at top, and then maybe we add a vertical line and then squeeze it, and that becomes a 9. What could be an 8? 8 could be 2 circles on top of each other, and then we squeeze. That's how we try to think. The thing, what we're trying to build is, we're trying to tell a network, hopefully you will learn patterns like this. If we see an 8, what the network will probably, hopefully, we try to determine whether there are 2 zeros on top of each other or not. So this is what the main task is. Pattern recognition. So from images, we go to pattern recognition. Okay. So now next time you take an image, maybe you can think something different. So that part is here. How do we think about images? You take an image, okay, you see some very colorful images, a landscape, someone is safe, you're having fun, etc., blah, 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 whatever is going on. But how do we think about images in terms of computer, in terms of mathematics? We think of this as like a data structure. So in Python, if you're using Python, there are different types of data structures. It could be a list, just a series of numbers. It could be array, like a matrix, like a 3x3 matrix, and etc. Something called a dictionary. We don't deal with dictionary now, so no, not necessary. So the way we think about images is something like some numbers arranged in 2D or 3D data structures. This will be clear very soon. What is a 2D data structure? What is a 3D data structure? The images that you take with your phone or camera, the pixel values are always greater than 0. What is a pixel? Okay, on the next slide. So usually when we take images, if the number is close to 0, so this would be recognized as a dark pixel. If the number is close to 255, this would be almost like a white pixel. But what is a pixel? So here is an image. It's a very, very, very primitive image. The way we think about this image, it is like a 2D or a 3D data structure. The 7x7 is actually the pixel. 1, 2, 3, 4, 5, 6, 7. On the vertical also it's 7. So these small blocks are called pixels. So here you can see it's almost like a smiley face. So what we expect that these black pixels will be 0, the white pixels would be 255. These are called binary images. Numbers between 0 and 255. Only 2 numbers, 0 and 255. We can normalize, then it will become 0 and 1. Binary. 1 for white, 0 for black. Okay. So let's try to put those numbers. It looks like this. Okay. It's still like a 2D structure. What we want to do is, we want to turn this into a matrix. This already looks like a matrix. I don't know if you know a matrix or not, but this is like an array. So let's try to put this in a matrix. It would look something like this. So now if you see this one, a matrix compared to the original image, it will be very difficult to figure out that this is actually a smiley face. Even for such a simple image like this, just from the number, it is very, very difficult to recognize that this is an image. So I hope you kind of are getting accustomed with the problem. Instead of images, if we just deal with numbers, this would be very, very complicated. Let's see some other examples, something like from 0 to 255. Some grayscale images, something like this. Instead of only 0 and 1, we have some other numbers in between. So 0 for black, 255 for white, and some other numbers in between. This, of course, can also be a matrix if I put the numbers, and the matrix would look something like this. Again, we are dealing with numbers. But so these images are black and white. What about the images that you take with your phone? Something like a color images, something like, let's say this. You have green, blue, whatever, many different colors. So this image is also, again, 7 by 7. But what we call for this image is something like a channel, 3 channels. The images that you take with your phone or with your camera, this will have 3 channels. So this 3 channel represents the red, green, and the blue color. Whatever the color we get by combining these 3 numbers, red, green, and blue. So let's try to put this, how this would look like. So this would look like, if we focus on the green pixel, so of course for the green channel, the numbers are higher. Almost nothing for the red, some very small values on the blue. So now you can make a guess. What would happen for the black pixel? What would I get for the black pixel? Take a guess.
Everything together.
Yes. Everything together. You can tell for separate channels what would happen. You can tell even for separate channels. If we just focus on the black pixel, what could be the numbers? So let's say for green, we got 200 for green channel, almost nothing for red, some very small numbers for blue. If we focus on the black pixel, what would be the numbers? You know what are the values of black? Usually, it's absence of a number, right? So if we indeed go to black pixels, it will be all 0. Okay, so now you have to make a guess. What about the white pixels? Everything 255. Perfect. So now you can proceed like this. You can get a 3-dimensional array. So I click all the numbers. So now here are the white pixels, 255. There was the black pixel here. Here are the green ones. Okay. So we moved from 2D data, from black and white, to a color image, what you're taking with your phone. The way we try to analyze this data is we do something called, in computer program, it's called a stacking operation. So we stack these channels on top of each other. And this becomes a 3-dimensional image. Now that's pretty fascinating. So what we will be dealing with, if you're dealing with a color image, we will be dealing with series of numbers in 3 different channels, R, G, and B. And if you see an image with some dimension, something like X, Y, Z, what it usually tells for the X, either you get the height or the width of the array. For the last one, for the 3, it usually represents the number of channels. Whenever you see a 3, that means, okay, this is the color image. If you see a 1, that means it's a black and white image. Okay, so let's try to see some examples. So let me switch to a notebook if I can. Okay. If I can open it. Does it open? Okay, it does open. Okay, so these are very simple, small Python scripts. So what you're seeing here is first, of course, you can check the functions that I told you, this tan hyperbolic function, the ReLU, etc. They actually make sense or not. So I try to plot them here. This you can try later, but let's focus on the images. So I load this handwritten data. So this is the loading function, and I'm trying to inspect a particular image. So I choose the index number 67. What you see on the data this first number, 60,000. 60,000 here signifies the number of images that you have on the day. The 28 by 28 is the 7 by 7. You have a 28 by 28 array. Okay, so let's see how does this look like. This is again a black and white image, and you can see that the central part of the image has some numbers. Can I try to zoom out? Let's see. Okay. So if I try to zoom out, to me, it seems almost like a 7. Here are some numbers. If I draw a diagonal, something like this, to me it appeared as like a 7. But it turned out that it's actually a number 1. So let's see if I can go down. Yes. When I try to see the image and the corresponding level, then it tries to appear as number 1. So this is an example of a black and white image. If we go to a color image, this would be even more complicated. Okay, so now I load some color image. That's the loading function. Again, you have 50,000 color images. 32 by 32 is the array size, is the dimension of your photo, and 3 channels. The other part, this 50,001, they tells you what the image actually is. In this case, of course, you can probably understand from the image that this is a dog. So let's see how does this look like in an array. Now you can see it looks like a pretty bad way of arranging numbers. So the dog that was visible before, now it's completely gone if you just see the numbers. I think let's, okay. I think next time when you take an image or you are dealing with images, please be mindful that our brain is so fascinating in identifying these numbers. So the light falls on me, it comes back to me. What I'm getting is basically some intensity values. And my brain automatically, very fast, interprets almost all the things so well. But we have to do this for a computer. How do we do this for a computer? Okay, let's see. So what we have learned is that images we can think about is like a 2D or a 3D data structure. 2D if it is a black or white, 3D if it is a colored image. So how do we now input this in a network? Okay, so let's see an example. Okay. So now before I go to the example, I think it's better to spend some time doing some very simple mathematics. How does the network learn? Or what exactly signifies learning here? What we are trying to tell the network. So, in general, in the AI community, there are 3 types of learning. So the first one is called supervised learning. Something like you have an image of a cat, and you tell the network that this is an image of a cat. You have a number 8, you tell the network that this is number 8. Then you show some unknown images, and hopefully the computer learns. So this is called a supervised learning. You supervise. First you train with some known data, and then you show the network some unknown data. Okay, the other one is called unsupervised learning. You don't tell the network anything, so you just give the network some images of dogs and cats, and hopefully the network automatically learns to separate the dogs from the cats. This is a slightly complicated task. The other task is the one that I discussed, is something with, let's say, the protein folding problem, the matrix multiplication problem. These are called the reinforcement learning, heavily used in robotics. So the way it works is, you have a robot, you leave it in the classroom, you just tell the robot to go to the end of the corner of the room without getting hit by any corner in the wall and etc. You don't do anything else. The robot automatically learns the path to go there in the shortest distance over time. It hits on the wall, it learns to not hit on the second time. Hits on the 10th, learns again the notebook on the shelf, and then finds eventually the shortest path at the end. This was the same principle that was used for alpha chess, the chess engine that can beat anybody. The same for AlphaGo, the same engine that can beat anybody in the game Go. What I will focus on is the easiest one, because this is very, very easy to go through. So this is called the supervised learning. So we are now in the era where we have huge amount of data. Most of this usually comes from internet, social media, and etc. But also what we have is a very, very advanced data processing units. One of them is called the GPU, graphic processing unit, for processing data very fast. It's not a CPU, it's a GPU. The feature of GPU is that you can run multiple same operations at the same time. So you can think about GPU as like very, very small CPUs trained for only one kind of task. Maybe let's say a multiplication, etc. So what our task again would be, again, just like the numbers, would be to identify features. So I got this slide from my colleague in Amsterdam University. This is a very, very cool slide because lemur is very, very easy to identify. At least for human beings, we can identify a lemur just by seeing the eyes. So in the back in the day, maybe let's say in the 1950s, 1960s, what would happen is like you train some filter to identify, okay, are there some black dots around the eyes? And suddenly you change this to a white fluffy hair. Maybe that's a lemur. So that was very, very old time back. What we want to do is, we don't want to generate any particular filter. We expect that the network learns the feature automatically. So that's the main idea. Why do we want to do that? So let's say if we generate filters for lemur, but if we show a monkey, maybe it doesn't understand that it's a monkey. But identifying the feature by itself, hopefully the network can distinguish between a lemur and a monkey. This is the main idea. We train a network to automatically learn the features. How do we do this? So this part contains slide mathematics, 6 or 7 slides. So bear with me. But this mathematics is very easy. Again, when that is for second grade, I think it should be very, very easy. It's not tough at all. So how does this network learn? Okay, so first thing first is that what we see here is a series of numbers that are going on in the network. But I say that I want to deal with images. But images are 2D numbers, 2D arrays. So something like this. We have seen the 7 by 7 images. So these are called 2D arrays. So this will not be accepted on this linear list. The way we do this is something called in Python, it's called flattening the array. So we have an array like this of 2D array, we flatten the array, and then we input the numbers. Okay? So at least we know what is on the input layer. We have the pixel values from the images that are going on in the input layer. Great. So input layer consists of the pixel values from the images going on there. Okay. So now, how do we learn? How do we tell the network what to learn? This algorithm is one of the most fascinating and it's so simple that it's so fascinating. So this algorithm is called gradient descent and backpropagation. Why it is called backpropagation? I will tell you very soon. So we are dealing with MNIST data, which is this handwritten data. So these are binary images, 0 and 1. We input the numbers of 0 and 1 on this input layer, and then let's see what actually is happening. We build a network, something like very similar like this. Have an input layer and have some dense layers. Let's see. So here I show you how to build a network and how exactly does it look like. So let me get out of this one more time. If I can switch back. Yes, great. Okay. Okay. So by the way, all of these notebooks are available to you, so you can just try by yourself. Okay, so this is where I try to build the net. I use the library called TensorFlow. TensorFlow is developed by Google themselves. You don't need to know what. Just see about this part. What I did is I have something called a dense layer. Dense layer is something where you have every node connected to every other node. That's called a dense layer. You can see the activation function. That is the value activation function, which is this one, the one that is written on the board. Then eventually we have something called an output. We have only one layer in between. So this layer is the input layer where the numbers are going in. We have one layer in between, and then we have the output layer. Let's see another image. So I try to plot it here using the function. So this is my input layer, two other layers, and then there is the final layer. What we are trying to expect is the final layer. So the final layer will tell us some numbers between 0 and 9. Because our input data is consisting of images of 0 and 9. So the final layer will tell us what is between 0 and 9. What is my input? The main calculations are going on here. You can check how I calculated the number of parameters for this network, but I try to write it here. Where is this? Okay. The number of parameters in this network, a very simple network. Input layer, two layers in between, and the final layer. Even with a very simple network, it has about 25,000 parameters. That's a big task. So what we are trying to do is we are trying to optimize these parameters so that the network learns a 0 is a 0, a 2 is a 2, a 9 is a 9. So now you can understand the complications of this kind of task. Is that we have to optimize huge number of parameters. And when I say huge, this is one of the simplest networks that you will find. Something like, let's say, ChatGPT, I think it has about 15 billion parameters. This only has 25,000 parameters. But it's still a lot of numbers, especially when you're getting started with. It's a lot of numbers. Okay, so let's see. Perfect. So what our idea is, okay, so we have a network like this. The numbers are going in. By the way, can I tell you what is this 784? Where is this 784 coming from? You probably didn't notice, but the input data has shaded something like this. So 28, 28, 1. So that is our image. So the 784 is just the multiplication of this. 28 times 28 is 784. It's because from the 2D array, I have flattened the array. So I started from the 2D numbers. I have flattened this array. So here it was 28 times 28. Here it is 700. That's it. And then we have some parameters in between. What we're expecting, if we give a 4, hopefully the final layer that signifies number 4, hopefully that lightens up. Hopefully that has some major number out there. Okay. This network has 25,000 parameters. So how do we train this network? So before I discuss the algorithm, let's go back to what was going on. So as I said before, let's just consider one node in one of the hidden layers. First, we start with the simple linear operation. W1 times x1, we don't call x1, we call this as activation. And then we add all the numbers. So this is the linear function. Then we add this non-linear activation function. These W's are called weights. This parameter is called bytes. And the sigma is the non-linear activation function. So very simple. We start off with a linear function, y is equals to ax, add them up, it is still linear. Then we add the non-linearity, and That's what would be there on that node. Okay, so we start off with 784 parameters at the input there. Then we have some other numbers. When we start the network, so let's say when you program the network and you start, let's say, train the network. When you press the button train, what will happen is that every layers in between will be randomly initialized between any number between 0 and 1. Our idea is that from these random numbers, it will be so well trained that they will get some particular numbers in between this W1 and this WN. Whenever I change from 4 to 9, the network is still capable of learning what is a 9. So how do I do this? So I do this by defining something called a cost function. So the idea of the cost function is something like the way you train a baby. So let's say you show a baby, okay, this is 0. The baby says, okay, this is 0. Then you show a different type of 0 and the baby says, no, this looks like 9. Then you scold the baby, hey, this is wrong. This is still the 0. So we want to do something similar like that. So the idea of the cost function is exactly like that. If we input a 0 and the network predicts 9, we tell the network you are doing very bad job. You need to do better. How do we do that? Okay, so let's see. So the way in general we do kind of optimization problem is, if you are again in bachelor's first year, you should know this is something called the first order derivative of a function. So that's the minimization condition. So we have a cost function, which is I call as C. C depends on the weights of the network, W. Then I take a derivative with respect to W, and then that's it. Set it up to 0, that would give us the minimization condition. This in physics is called the rolling down the hill problem. So this is the landscape of the cost. The minimum is somewhere here. And if you know, again, if you're in physics or mathematics, you know that this part is where the tangent is parallel. That is the condition for this del C over del W becoming 0. Okay. So what we are trying to do is trying to put the network parameters somewhere in the minimization landscape, defining a cost function. But how do we do this? We have a big problem. The problem that you see here is very simple. Something like, let's say, you're in bachelor physics first year and you want to know what is the maximum velocity of a car to reach some particular value. Then you can calculate this by a simple function like this. Depends only on one parameter. The cost gives something like this. But the moment you go to a multidimensional function, in this case, our network has 25,000 parameters. The cost function looks very complicated. It's a multidimensional parameters. I think it's shown here with only in a 2D plot, but it is not a 2D plot. It's like a 25,000 dimensional parameter, because that's the number of parameters in the network. And then it becomes very, very difficult to really figure out the minimum here. Where exactly is the minimum? So we call this in AI community, we usually call this as we roll down the hill, but now we are stuck in the valley. So we are walking in the valley, up and down, and we're trying to figure out where is the minimal point in that valley. Sometimes it's very, very difficult. So the way we try to do is to start from some initial value. Let's say we start from some initial number of W's, the weights of the network, and then we have to tell to the network, either you go to the right or go to the left. If you go to the right or go to the left, how will you go there? So here comes the training part. So we want to guide, let's say, our weight either to here or here or here. If we start from here, we can tell the network to go down, so the weight go down here, or it might come down here. But how do we keep the weights here? How do we make sure that the weight doesn't jump up or jump down? So this is the mathematics part. This is very, very, very cool how it actually is done. So the way it's done is shown in this animation. So we start with the number, and as it is getting close to the minimum, we will tell the network to go slow. So we take the derivative of this function and we tell the network if the derivative is high, somewhere like here, it's a perpendicular. Then we take bigger steps. Then I tell the network you can change the weights by very, very high numbers. If the derivative is small, something like here, the derivative is small, about almost half, then I tell the network, okay, the derivative is small, so take smaller steps. And as you take smaller steps in between here, you are now more closer to find the actual minima around here. So it's a very, very simple trick, but very fascinating. That you just take the derivative and you use the value of the derivative to guide the network where exactly is the minimum. We take care about the slope, and if the slope is high, we tell the weights, okay, take bigger steps, take more changes. If the slope is low, we tell the network, okay, just take very small steps. Okay, so it has about our network again, as you have seen on the notebook, it usually has about 25,000 parameters. So it's not a single variable calculus, it's a multi-variable calculus. 2 more slides of mathematics and then I'm done. So how do we deal with this kind of multi-variable calculus? Again, if you go back to bachelor's first or second year, what we do is something called, instead of taking a derivative, we take a gradient. So I don't know how many of you know gradient or not, but gradient is taking derivatives for multiple functions. So we take the gradient of this cost function. So here is a simple example of a 2-variable function, x and y. If I want to take the gradient of x, then I just take the derivatives with respect to x squared becomes 2x. If I take derivative with respect to y, this becomes 2y. And this is my gradient 2x and 2y. We are doing exactly the same, but instead of 2 variables, our network has 25,000 variables. So our gradient matrix would look really, really big. And this is the main idea of the supervised learning. When we say supervised learning, minimizing the cost function is basically the way we tell the network is actually learning. So now, what is minimizing a cost function? Okay, let's see. So that's our gradient matrix. Let's say we have about 25,000 parameters here. This is what we want to optimize. So what does this number signify? So these numbers have 2 significance. So first is the sign. The sign tells you whether you go left or the right. The values tells you you have to take small steps or bigger steps. If the values are higher, let's say here, that particular weight has to be changed a lot. If the value is lower, that particular weight needs to be changed very, very small. Again, 25,000 weights, they're constantly getting updated. As I show images, I tell the network, this is 0 input image, you have to tell 0 output. The network learns, okay, this looks like a 0, then again for 9, for 5, etc. And these weights get updated as time passes. And this algorithm is called backpropagation. Why it's called backpropagation? 1 slide of mathematics, and then I'm done. Okay, so the way we try to think about this, let's say we input an image of 2 in this case, yes. So, and we get an output number of 0.2. That's a very low number. We want to make it as close as possible to 1 at the output level. So we have to increase this number close to 1. Then we know that this input image is a 2. If let's say we input a 9, for this one, it has to be, for this last layer around here, it has to be very close to 1. Then I know that the input image is a 9. In this case, it's a 2. And the number is very less, the output is only 0.2. So we have to make a nudge on this one. instead of 0.2, if it is predict 0.8 or 0.9, that's better. So the way we do this, we can either increase the weights. Weights are the connection from this to this. Or we can change the activation. We can change this value itself. So how do we do that? Here comes the definition of the cost function. Okay. Don't get confused with this very weird definition. What is going on? Again, it's very, very simple. So what you see here is the output, the z we call the output. This is the linear function. Y is equal to mx plus c. So this is our weight. This is the activation coming from before. And then the corresponding bytes. The L represents the current layer. L minus 1 is the activation before. We are focusing on this layer. So this layer is denoted with L. The activation from before is denoted with L minus 1. WL are the connection, the weights, and you get the final activation P. So this is the calculation. And the way we try to write this, maybe even more clear, if you do something, deal with something called a graph, it will look something like this. WL, AN minus 1 BL, they combine to produce Z. Z is then used with the sigmoid to give you the final activation. Okay, so what is our cost function? Let's see. So the cost function, we think about something like a mean squared error. So let's see an example. So let's say again, take the example of this 2. So for 2, if I give an input image of 2, I expect that the network predicts at the output layer for that particular node to be high number, maybe 0.99, 0.95, something like this. But instead, the network predicts something like, let's say, 0.3. So this AL is the network output. Let's say 0.3, and this is the true level, because I know when I give the input, what am I giving? Here it will be 1 for the particular 2. And then we just take the difference, 0.3 minus 1, 0.7, take a square. That is our cost function. Okay, we want to minimize this cost. But here is the problem. We say that the weights, the connections are very, very important. But if you want to take a derivative of this cost function with respect to the weights, there is no connection between cost and the weight. Anybody, if you're studying physics again, do you know how does this actually work? Any idea? If you don't have a direct connection from one variable to another, then how exactly do we do this? So, okay, if you don't know, this is the very fundamental principle of multivariable calculus, and this is called a chain rule. So the chain rule, the way it works is like, okay, we figure out that C is connected to the activation. Activation is then connected with the Z, and then Z is actually connected with the W. So that's what we try to do. Calculate the cost with respect to the weight. First, we figure out that the Z and W are connected here, then A and Z connected here, and then finally C and A connected here. If you don't know, don't worry. It's called the fundamental principle of multivariable calculus. The two variables are not connected. We try to find the chain, how they are connected, and then we take the derivative. So we always have this joke running around from people studying computer science. They are doing artificial intelligence, or somebody studying mathematics or physics, they are doing artificial intelligence. So for mathematician, it's like a big Shiba Inu on steroid. You know? He knows mathematical optimization. He knows very well matrix multiplication, etc. But somebody coming from computer science, that's a very sad Shiba Inu. He doesn't know what's exactly a chain rule. So if you want to study, I think deep learning, I think it's better to be this kind of super, where you know at least what are the basics, what exactly is going on. Okay, so finally we optimize the function. If you don't know the derivatives, don't need to care about this. What we want to do, finally, after we figure out the derivative with respect to the W, we do the same with the bias and the activation. These are the three parameters in our network. W, weights, activation, and bias. All combined together at this 25,000 parameters. We try to optimize, and that's it. This again is another example from, I think it's from Berkeley or somewhere. I think it's written here. You can check the GitHub. I think it's from the Berkeley website. So how does this look like if I want to plot? How does the step size look like? So we take these steps as we are away from the cost function. As it approaches the minimum, then it takes very small steps towards the minimum. Very nice way to represent what is exactly going on inside the network. When we are away from the minimization points, we take bigger steps. As we are getting close, we take relatively small steps. And the network hopefully optimizes to some very nice values. Okay. So what has gone on so far? Okay, at least we know what is a neural network. The neural network is something like a complex mathematical function. We have linear operation, then we add some nonlinear operation, and hopefully through some optimization, this kind of works for a particular task in hand. Maybe let's say an image recognition. We of course probably have an idea when you see an image, especially think about this again, the next time take an image. And how fascinating is this that try to think of your car or your friend's face as like a block of numbers. Then it would be very weird that this block of numbers looks like you as a face. This block of numbers looks like you as a tree. Very weird. Because that's exactly what is going on in the computer. That's exactly what is going on in the brain. And somehow our brain figures it out. We learn very primitive way the main algorithm. It's called the gradient descent and the backpropagation, and then we can train the network. So the network part, this again is uploaded on the timetable. Just try to run the network if it makes sense or not. So I think, okay, let me see if I have some examples. Yes, yeah. So okay. So you can just run it from here. So I train the network. It feeds to the data, and then we can predict. So let's see some prediction. Okay, this part is very good. The network does something very good. So let's say an image of 8, the network predicts 8, 1, predicts 1. Sometimes it makes mistake. So I show an example of a mistake. This mistake is here. The true level that I give to network is 8, but the network predicted 9. But I hope that for you it kind of makes sense that why it looks like a 9. Because indeed it kind of looks more like a 0 and then a vertical line here. The more you see images like this, you would understand that what is actually going on within the network is that the network is trying to learn different patterns. Maybe for this one, the network thinks, okay, this is the zero here, this is the line here, to me that looks more like a 9. So I predict 9, but the actual level is 8. Sometimes, most of the times for this task, it would do very good. Sometimes it makes some mistakes. So run this by yourself and it would be more clear for you. So usually what happens, it's now exactly 1 hour. So we usually take a break in the class because we have done so much.
Do you want to sit down and rest a bit?
No. Usually in university also it's like 1.5 hour class. Okay. So
That 8 looks like 9 to me.
say that again?
That 8 looks like 9 to me. Yes, that 9 looks like 8 to me.
Okay, I guess if I take more break, I think it will be very difficult to finish at 3. Okay. So after this presentation finishes, you can always check back the images and check back how this network is run and etc. So we have in general one big problem. The way we train the network, it has a big problem, and this problem is that we have an image like this. So when you take an image, it's basically a 2D image or a 3D image like this. Whenever we see an image, you see the images like this. But if you see a network, we input the data in a list format. Nobody understands what is going on this list. If I show you a list, you'll never be able to recognize. If I show you numbers like this, maybe you can recognize. So, can we input numbers like not like this, but like this? So this was the idea of something called the convolution. The other part of this is that when we try to connect every node to the other node, it creates exponential connection. So here is an example. So let's say the network that we trained has about 25,000 parameters. But that's a very, very bad image. It's like 28 by 28 pixels. Nobody takes images like this. If you see on the computer screen has about 1024 by 768. If you take an image with your iPhone, it would be something like, I think, about 800 over 720. So that's a lot of numbers, 800 times 720. If I just increase from 28 to 100 and try to connect this 100,000 parameters to the next 64 neuron network, only with one layer, the number of parameters would be 2 million. Now that's a big number of parameters. That means we need more resources and we also need more time to train the network. Can we get out of this? It turned out we can. And this is called the convolution. So I suggest we go to the Reginna website and go to the first summer school. And there was a very, very nice lecture by Laura Roberts. This slide contains very, very beautiful description about convolution and how it's done. I just tell you the very, very basic principles, how it actually works. So the way it works is you see a mathematical function. Okay, let's remove this. The mathematical function is very complicated. We say f is convolved with g, and the mathematical function is something like this. Well, that's a very difficult thing, especially if you're not into integration. That looks like very complicated. But let's see an image, how exactly it is. So we start off with a function like ft. So let's say that is our ft, and this is our gt. We want to convolve these two functions. So first thing first, we turn gt to g minus star. So we go here. We take just a mirror reflection. So this one is just a mirror reflection of this. So we change from g of t to g of minus t. So you can always remember something like this and a function like this. They are just a mirror reflection of each other. Exactly the same operation is done. From t we change to tau, but the main point is that it's a mirror reflection of each other. Then what is convolution? We slide it at t minus tau. So equal to t, we slide it at t minus tau here. And then we just go over each other. What does the go over each other mean? It means we try to multiply the number and add it up. And that is the integration. So let's see an example. If it is still not clear, let's see through some numbers. What is actually convolution? Very, very important in signal processing. So here is an example of convolution. So let's say we start off with this two lists, 1, 2, 3, and 4, 5, 6. So how we will do it? So first we take a mirror reflection, 4, 5, 6 becomes 6 by 4. We slide it up 3 numbers, we slide it up to 3 numbers. We start and then just take the multiplication. So you can see it here. Okay, let's go back. So let's say if I start from here, it's basically 4 times 2 plus 1 times 5, that is our 30. Then it goes up again. So the fourth one would be 4 times 1, none other matches, so that is our 4. This is very, very simple. and very easy to do in a Python code. Just use something called the mathematical operation, numpy times 1 more, you would get back the exact thing. And that is convolution. That is the one of the most used principles in signal processing. Image, audio, data, everything is done with this sort of convolution. Okay, so this is a 1D array, but what we want is a 2D array because we are dealing with images. So for 2D array, from a list, we change the array. And then we slide the filter on top of each other. We do the same performance. What we do? We do the matrix multiplication of this matrix with this, add it up, and then get an output. Very, very simple. Just matrix multiplication. We always joke that 99% of the artificial intelligence is dealing with matrix multiplication and very simple linear algebra. So this you can see an example here. Think of images as like matrices. We take another matrix, we call that as a filter. We slide it over, basically matrix multiplication, and then we just add it up. So what we're expecting is that some of these filters will learn some features. What does that mean? Okay, let's see an image. So take an image of a dog, and I try to slide, let's say, this vertical filter. The V is for vertical. So I try to run this vertical filter, and then you see that the vertical edges are getting detected. A horizontal filter looks something like this. You can see this horizontal part compared with the vertical part here. The horizontal parts are more lightened up. So we were expecting that after training, our weights would look something like this, so that we can identify. Of course, the edges of a dog head would look very different from a cat's head and close to eyes and etc. So that's the main idea. We try to train different types of filters, but we hope that the network automatically learns this kind of filters. As I said in the slide before, instead of making our own filters, we want our computer or our network to learn filters by itself. The network looks something like this. We have an input image, and we again, before what you have seen, something like nodes and then connected densely. But here, these are all matrices. So these are way more meaningful operations. What do I mean by more meaningful operation? So this, I have a link for my notebook on my GitHub, so you can check this. You can also run this by yourself. So let's say take an image of a cat, and what you see at the very initial part of the convolution, it detects the bigger features, something like, okay, lightens up the cat, maybe detects some bloodiness in the cat, or etc. But as it goes down, as we go deeper in the network, so let's go back to the previous one. So here, let's say we detect the easier features, maybe the brightness, etc., etc. But as we go deeper, maybe it learns the whiskers, maybe it learns the nose. That kind of like, that's okay, you can see the structure of the face, the very weird shape of the ear. And this is so cool to see that actually after we train the network, we can print out this weight matrix. And the weight matrix looks something like this. It's so fascinating to see. You can go to the GitHub and run this by yourself. Some other complicated network that I worked on is something like, let's say you take an image, series of images like this, and let's say I take one of the images and put it here. Every image corresponds to change like this. I hope it makes sense. So let's say I start with this lady, she will look like this, and a 5-year-old kid, and then a 20-year-old lady, something like that. These are my inputs. This is a test data. So let's say I take one of the images here, and eventually they will look like this. So this type of networks are called generative networks. They can generate data by itself. So this was the, like about 5 to 6 years back, this was really very promising. But now, of course, we have something called ChatGPT and DALL-E. They're way more advanced. What I want to discuss in this last 10 minutes would be this particular type of network that are used mostly in self-driving cars or in robotics. So what you see here is I think it's from the Tesla website. So you have a camera in front and it sees something like this. Of course, it's an optical camera. What the network within the Tesla car is trying to detect is trying to identify every pixel in the image. The pixel that belongs to the tree, the pixel that belongs to the road, and etc. etc. This is very important, especially for preventing accidents and etc. This was early days. It's not done like this exactly now, but this was like 2018, 2019. These techniques are called segmentation. So here is an example. First one is called an object detection. So let's say you have an image of dog and cats, and you can make a boundary around the dog and the cats. The other one is segmentation, where you segment every pixel that is belonging to a human being. So these are heavily used in automated driving cars. But this turned out to have some other usages. And one of the network that got so famous is called the UNet. Now I think it has more than 70,000 citations by other researchers. It became so famous in the segmentation. So here you can see an example. Mother driving the baby on the steering wheel, and it tries to segment every pixel that belongs to a human. And that's the result. So these are heavily used now these days for object detection tasks. And one of the tasks is something similar like segmenting biomedical images. The nuclei, you give an image of a sample. The sample contains some fluid, microfluids, and some nuclei. The network automatically can detect the nuclei. So this is the final hands-on segmentation. Let me see if it is open or not. So this is also available, and you can of course try this. Let's see, is it this one? Or is it the other one? Yeah. Okay. So you can run this again by yourself. So what you see here is like almost like a low light images of nucleus here. So first, some doctors and the students, like in the first and second year, they first label the cells. So the network first learn which pixels belong to a cell, which pixel belongs to the background. Then you give some other images, and the network predicts very, very well. So these are now heavily used in biomedical tasks. Yes, you can run the whole thing by yourself and check some example prediction. So this is a test data. Test data is something that the network has never seen before. So this is the random nuclei images. You can see it predicts very, very well. So we have seen an example of a biomedical image segmentation. Nuclei are very small. So I remember when Yuri came to me. I think all of you know Yuri, right? So when Yuri came to me, he was telling me, Dr. you have to give a presentation on deep learning and possible applications of nanomaterials. I'm like, okay, I don't know what nanomaterials, but I was thinking about this. With cell segmentation. So immediately in front of him, I searched some examples of nanomaterials. It's unbelievable that the same network that was used for the Tesla car, the same network that was used for the cell segmentation, the same thing was used for nanoparticle detection and object tracking in the network. So you can check this network, so you can check this paper. So this was published in Nature, one of the most reputed journal. Let me see if I have this open. It's on this one. Right, exactly. Can you see? Yes, okay. So you already have this network available to you on a notebook. Exactly the same network. UNet, it tracks the nanoparticles. It's unbelievable. Just by doing a 2-minute search, I can find this one. And that's what I want to convey to you is that the application of deep learning is like usually doesn't depend on your domain knowledge. If you know the mathematics and if you know the applications, how to write code, how to make this data suitable for your network, you can apply it to many different contexts. So let's go back finally. The same thing was applied again on something like the object detection technique, not a unit, but object detection technique was applied on something like finding the suspended particles in a nanoparticle solution. Very fascinating. The other one that I found that people uses a lot these days is called this transmission electron microscopy. So this network is very useful for dealing with particular set of images coming from the transmission electron microscope nanoparticles again. Again, it's completely based on new nets. It's very fascinating to me that there are so many papers that are working on the same subject, and the usefulness is so high. The best thing is that you have the network. Once you go back again, you can find this on the timeline. Everything is uploaded, all the notebooks, the presentation. You can just try to run this by yourself. Maybe for a summer project, or maybe next summer, you can try this to download the data, something like a nanoparticle detection on images, and then let's try if the network works or not. And many other applications that I didn't discuss, something like generating new materials, something with a probabilistic network, and etc., so many more. Finally, to end the presentation, so what I do mostly, I thought I should tell you this. So I mostly deal with astrophysical images. So this is the gamma ray image. So this image is coming from a satellite that's about 500 kilometers above the sun, above the Earth. So let's say the International Space Station is about 450 kilometers above the Earth. This one is about 500 kilometers above. And it takes the images of the gamma ray sky, not on the optical wavelength, not what you see with your eye, not what your phone captures, but particularly gamma ray wavelength. And what you see here, these small dots, most of them are extra galaxies, other galaxies, far away from us. Some of them here are something called a very fast rotating stars. They are called neutron stars or pulsars, and they emit gamma rays. And this got detected by this satellite. So what I try to do is I try to apply something very similar, and I try to detect what kind of galaxies are involved here. How can I identify these galaxies and etc. And that's the main, that's to me very fascinating, because when I look back at the nanomaterial images, if you're working in the biology or nanomaterial sector, you can think about the small galaxy as a cell. You can think that small galaxy as a nanoparticle, and you can apply the same algorithm. And that to me is very fascinating. Also, I wanted to show you another picture. This is another sky image, but instead of the X-ray, instead of the gamma ray, this one is X-ray. So when you go out on the tunnel, you're watching the night sky. This again, try to think that first of all, you're seeing basically some numbers, the lights that are coming to you, and also what you cannot see through your eyes. This you will never see, because our eyes are only sensitive to optical wavelengths. If we go to something like gamma ray and the X-rays, they will be very different. Let's finish the presentation. I hope the presentation was interesting, but also with the materials, hopefully you can go back and try to run some of your books by yourself, and hopefully it can lead you to something new. At least when I was in a new age, it was like whatever I was interested in, I would like to try them as fast as possible. And hopefully maybe by next summer you have something more new to try. So to finish the presentation, I always say that you are the one that decide what you're gonna do. Hopefully if the presentation is interesting to you, try something for yourself. Thank you. Any questions?
How did you go into this stuff?
That's a long story.
Okay, when did you go into this stuff?
Well, so let's say for this one, I'm working for let's say about 4.5 years, 5 years. But before I was mainly working on very, very core astrophysics. Something like, have you heard about supernova? Supernova. A star bursts, the star goes, become old, then it becomes big, and it creates an explosion. It takes some particles, let's say electrons or protons. So I was studying how those electrons from the stars come to life. So this is very different. But it mostly came from the part that I was very interested in images. So I think it was a natural implement. Yeah, instead of now, before it was detecting electrons and photons, but now it's mostly detecting the gamma rays and the gamma photons. So these are basically photons, but again, not what you see, but very high energy photons.
Did you have a lot of free time in school?
Yeah, I think so. I believe in, so when I'm in the class, I always tell that one of the principles that you can have is something called do it fast. If you don't like the class, do it fast, the homework, so that you can have more free time. If you like it, you do it fast, so that you can go back and do something for yourself. When you're young, you have this ample amount of free time. I sadly, I don't have that much now. I wish. I think probably that's one of the best parts about being young. Okay, cool. So